Hello guys, I hope you all are doing well. Today I will be solving May Jun 2014 paper 119701 chemistry. So let's start. Question number 1. Use of the data booklet is relevant to this question. Atoms of element X have 6 unpaired electrons. What could be element X? Oh yeah, I should actually open my data booklet as well. Okay, so now I have my data booklet open as well. But anyways, the first option is carbon. Carbon has 6 electrons, so its electronic configuration then is 1s2, 2s2, 2p2, right? So 1s2, 2s2, 2p2, that means that, okay, so the s subshell anyways is, fully filled 1s, then 2s as well. Then as for 2p, that has 2 electrons that are unpaired. And that means that, yeah, you need 600 electrons, so it can't be carbon then. If you look at chromium, chromium is where in the periodic table? Yeah, it's here. So then, we go 1s2, then this is the s block, so 2s2, and then we have 2p6, 3s2, 3p6, 4s2, then 3d, this is the d block, right? So 3d, 1, 2, 3, 4. So 3d, 4. That is the electronic configuration for chromium. And okay, so we already know that 1s2, 2s2, those are completely filled, as is 2p6. It's going to be 1, 2, 3, and then 4, 5, 6. Okay, my drawing is not that good, but I think you get the point. Then 3s was also completely filled, 3p is also completely filled. Okay, I am pretty not good at drawing subshells apparently. But anyways, and then 4s is also completely filled, and then 3d4. 3d4, well, you have 1, 2, 3, 1, 2, 3, yeah. 1, 2, 3, 4 electrons there. But you need 600 electrons. And in chromium's electronic structure, it seems that you only have 4, but actually, you have to realize that, okay, so we have 4s2, 3d4. What chromium actually prefers is not to have a 4s2, 3d4 configuration, but a 4s1, 3d5 configuration. The reason for that, I think, is a bit complicated, or yeah, but yeah, you could just think of it as, it just 5 is a more complete number than 4, kind of, because it has 5 orbitals, right? So it's just more complete if it's 5 fully filled. Or in the case of copper, 10, like 10 electrons in the d subshell. But yeah, so it becomes 4s1, 3d5, so then you have 5 electrons there and 1 less in the s 4s subshell. So then now if you count it, then you have 1 electron here. It's highlighting, it's not working. Okay, 1 electron here and then 5 electrons here. So then 1 plus 5 is obviously 6, right? So then that makes 6. Because actually, yeah, chromium does not prefer the 4s2 3d4 configuration, but rather the 4s1 3d5 configuration. Similarly, copper does not prefer 4s2 3d9, but rather 4s1 3d10. Okay, so yeah, it seems that chromium does have 6 unpaired electrons. So we have 4s1 3d5, right? So 6 unpaired electrons. And so I can say that, yeah, chromium could be the correct answer, but we can still look at the other options. So we have iron and selenium. So iron is over here, so it'll have literally the same configuration as chromium up till the 4s1 subshell. This is the s block, this is the p block, this is the d block, and yeah, that's the f block. I mean, I guess you could um also use that triangle thing. I keep forgetting what that's called actually. Is it the wow, wow, yeah, Aufbau principle. I think it's the Aufbau principle, but yeah, which is quite useful, the triangle thing. But on the other hand, you could also just use the beautifully laid out periodic table, although there are other variations of the periodic table actually. Like this is the one I think kind of like IUPAC uses this one, but there are also other variations of the periodic table that look really cool. I mean, if you want to search about that, it's a really cool topic. Because I guess you could arrange it in different ways depending on how you want to use it, how you want, like what your chemistry passions are. But anyways, 1s2, 2s2, then we have 2p6, then 3s2, 3p6 for iron, and then you have 4s2, and this is it's B block, right? So then 3D 1, 2, 3, 4, 5, and then for iron, so 6. So 3D 6, 1, 2, 3, 4, 5, 6. Okay, so that is the configuration for iron, and yeah, again, all of these are going to be completely filled for S2, right? Because yeah, S has 3 orbitals, and then P has, sorry, S has 1 orbital and P has 3 orbitals, and then D, it has 5 orbitals, right? So I'm just going to draw the 3D 6, the 3D subshells of 1, 2, 3, 4. I'm going to divide this, and then we have 1, 2, 3, 4, 5 electrons that are unpaired, and then you have 6. So that's according to Hund's rule. You know, the only problem is I don't remember if I remember the names of the, I don't know if I remember the names of each rule right or not, but I think it was Hund's rule, right? Like, you know, it prefers pairing only when there's no other electron empty orbital left. Was that? Oh no, that was the Pauli exclusion principle. Yeah, I just studied this a few months ago, but then I never remember. Like again, at university with them, never remember the names, principles. Yeah, but anyways, I think it was Pauli exclusion principle. Anyways, I will stop saying random things, and the point being that okay, I drew the 3D orbital, and then I have 6 electrons there, and so how many unpaired electrons do I have? I have 1, 2, 3, 4 unpaired electrons for iron, and that means again it's just not equal to 6, so that means iron cannot be my answer either. Then we check selenium. So selenium is where? Here's selenium. Okay, so again it'll have the same configuration up to 4sm at least. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and then 3d 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's completely filled. 3d 10, and then you have 4p 1, 2, 1, 2, 3, 4. So 4p 4, if I'm not mistaken, is that's the configuration, electronic configuration of selenium. And yeah, so till the D subshell everything is fully filled apparently, and then for the 4p subshell, let me just draw it. Okay, I don't know why I drew it this big this time, but anyways, you have 1, 2, 3 orbitals, then you have 4 electrons in those orbitals, so 1, 2, 3, and then by Pauli exclusion principle, you know, they're all in separate orbitals first to minimize repulsion, and then you get pairing. So you have 1, 2, 3, 4 electrons divided like that, and how many unpaired electrons do you have? Well, all of these are paired, and then in 4p you have 1, 2 unpaired. So again, that's not equal to 6, is it? So that means selenium cannot be your answer either. So I'll cross it out, and then you only have chromium left over. That will be my answer. Anyways, let us go to the next question. Use the data booklet is relevant to this question. I have the data booklet. I don't think, because this is like, I don't know if you need it or anymore or not. I think now they don't really give you a data booklet, right? They just give you a periodic table, and if you need any data, they give it to you. But anyways, this is an old data booklet, 2016. It's fine. We'll use it because this is a 2014 paper. Iodine is a black, shiny, non-metallic solid and a member of group 7. It sublimes easily on heating to give a purple vapor. A sample of iodine vapor of mass 6.35 grams has a volume of 1.247 cubic decimeters when maintained at constant temperature and a pressure of 1 into 10 to the power of 5 pascals. If iodine vapor acts as an ideal gas, what is the temperature of the iodine vapor? So, what I can say is I have a lot of numbers and it is behaving as an ideal gas. So, whenever I think about ideal gases, I just think about PV equals to nRT, my favorite equation, at least it's the favorite equation of one of my professors. But PV equals to mRT over mR, okay? And then I can kind of, because I need the temperature, right? So I can rearrange this because I have the mass m. Of course, I have the ideal gas constant because it's a constant. And I don't have the temperature, obviously. MR, I know it's iodine, so I can get the MR, the molar mass. And then pressure, I also have, yes, and volume, I also have. So it's just the temperature, the need, and so I can definitely use this equation. So T equals to PV mR over m times r. Okay, so I rearranged this like this, and I will erase this so that I have some space. And now we will use this equation. I don't know why I'm changing the color, but I am. And then 1.00 into 10 to the power of 5. I feel like writing, I don't know why, I feel like canceling things today, like writing SI units and stuff. So anyways, pascals, that is equivalent to what? P equals to F over A, right? And force, that's in SI units, that's kg. The newtons in SI units is kg m s to the minus 2, I think. And then area obviously is m squared, meter squared. So then this cancels with this, so you get kg m to the minus 1 s to the minus 2 as the unit for pressure. And yeah, I don't know why I'm doing this, but it's fun sometimes to do dimensional analysis. Yeah, okay, anyways, so that's 1 into 10 power 5 pascals. This is equivalent to pascals times multiplied by the volume, right? So volume is 1.247 cubic decimeters. So 1.247, now I want to convert that into cubic meters. So I multiply by 10 to the power of minus 3, right? Because 1 meter, there are like 1 meter equals to 10 decimeters, I think, something like that. Okay, so then if you want 1 decimeter, then you have to make it 1 over 10 meters, which is 10 to the minus 1 meters. And then since you have 1 dm cubed, for example, then that means you have to make it 10 to the power of minus 1 cube meter cubed. So that means the conversion is, if you want to convert from dm cubed to meter cubed, then you have to multiply by 10 to the power of minus 3, or you have to divide by 1000 basically. Anyways, that is that. And then I have my molar mass, which is 6.35 grams, but then again I'm doing it in SI units, so I can convert this 6.35 grams to 6.35 into 10 to the power of minus 3 kilograms. Okay, and then I divide this, and I will erase some stuff here because it's fun to erase stuff. Chemistry is fun in general, I guess. Anyways, then we divide by the mass. Oh, did I multiply by the? Oh yeah, okay. I made a mistake then. You have to divide the mass, right? So sorry, my mass should be down here. Sorry, to 10 to the power of minus 3 kilograms, and I should multiply by the molar mass. Yeah, molar mass. Okay, so what is my molar mass? Iodine. So iodine has a, okay, so it's molar mass is 126.9, the element. 126.9 is atom, 126.9. And then because it exists as I2, right? So then I have to make it 126.9 into 2. And good thing that my calculator is right here. That is 253.8 grams per mole. And now again, because I want it in SI units, I could make it 253.8 in 10 power of minus 3 kilograms per mole. Actually, you know what? I don't really need to do this. I will keep it grams per mole, and what I will do is I will also keep my mass in grams. So 6.35 grams, because then I can simply just cancel this and this. I mean, you could convert it to kilograms and keep everything in SI if you want, but I just don't feel like doing that at this moment, even though I did want to 3 minutes ago. Okay. Anyways, now we have to think about the ideal gas constant. So ideal gas constant is 8.3145 joules per Kelvin per mole. I don't know how much accuracy the data booklet states it to. Let us see. I can't even find it. Okay, I found it. Okay, it's 8.31. Okay, great. So I will erase two significant figures. Great. 8.31 joules per Kelvin per mole. Now, joules is basically W equals to FD, right? And W has the units of joules as well, work. So force times distance, that's kg ms to the minus 2 times m, so that's kg m square s to the minus 2. So basically, joules is equivalent to kg m square s to the minus 2. You don't actually need to do dimensional analysis, I just find it fun. And per Kelvin per mole, right? So that is the units you have for the ideal gas constant in this form. And I will erase some stuff again, and then we will just, why did my volume get erased? Okay, anyways, I will now calculate this. Please use your calculators, everyone. And I hope I did not make a mistake or something, but I get an answer of 599.768 kelvins. How do I get kelvins? Well, per mole cancels with per mole, and then meter m to the minus 1 times m to the 3, that makes it m to the minus 1 plus 3, which makes it m square. M square in the numerator cancels with m square in the denominator. Then your kilograms cancels with your kilograms. S to the minus 2 cancels with s to the minus 2. And so you only have 1 over k to the minus 1 left over, which is basically 1 over Kelvin, which is basically Kelvin, right? So that means, yes, you do have units of Kelvin. So our dimensional analysis was correct. Anyways, this is approximately 600 kelvins, and so our answer must be B. Okay, great. Now let us go to the next question. So enthalpy changes that are difficult to measure directly can often be determined using Hess's law to construct an enthalpy cycle. Which enthalpy change is indicated by X in the enthalpy cycle shown? All right. So here you have delta HF, and that's probably the enthalpy of formation of, well, the only thing you're forming on the left-hand side is CH4 gaseous, so that's probably that, right? Of course. And as for, well, this is obviously the enthalpy of combustion of the CH4 gaseous, this one. And as for delta HF that's shown here, that is probably the enthalpy of formation of, well, I mean, it's obviously going to carbon dioxide, so it's probably that of carbon dioxide. And therefore, X is going to be the enthalpy of formation. Well, you're forming something else as well here, which is water, liquid. So X is equals to, but then you're forming 2 moles of it. So it should be 2 times the enthalpy of formation of water, liquid, right? So that is what X is representing. And so let's see which option is correct then, but it's not 4 times because, well, you're forming 2 moles of the water. So yeah, it can't be 4, it can't be 4. 2, it can definitely be. But is it minus 2 or plus 2? Well, I'm going in this direction, am I not? So, I mean, it should be plus, should it not? Plus 2 times the enthalpy of formation of water. I mean, I don't see any reason for it to be minus if it's going from the hydrogen and oxygen side to the water side, and it's going in this direction. The X is the same direction as that, because the enthalpy of formation means that you're forming something. So it's not the negative, because negative enthalpy formation would be like kind of, I don't know, an enthalpy of, I don't know, what's it called, dissociation or whatever, I don't know. I don't know if dissociation is the appropriate word in this term, in this scenario, but then if it was like this, then it would be the enthalpy of it being unformed or dissociating. So then it would be minus sign, minus 2 times the enthalpy formation. But then this is the enthalpy formation. It's positive. But the enthalpy formation is obviously negative. But like I mean to say that it is in the direction of enthalpy formation, so it is positive 2 times the enthalpy formation. So it's the answer would be negative probably, but yeah. So it's going to be D. The D is the answer, and I hope that makes sense. Because yeah, I have a habit of saying a lot of stuff. Okay, now question number 4. The table shows the physical properties of 4 substances. Which substance has a giant covalent structure? Well, ideally, a giant covalent structure should have a high melting point and a high boiling point. I would say that A and B are wrong right off the bat. Then the electrical conductivity of the solid. Okay, so all of them are poor. I guess that doesn't really tell me that much. Um, and the electrical conductivity of the liquid, on the other hand. So you have poor, poor, good, poor. And again, that doesn't tell me too much. On the other hand, electrical conductivity of aqueous solution, that is quite an interesting factor because that tells me if it's ionic or not, right? So I mean, insoluble, good, good, insoluble, that means that good, good, those two are going to be ionic, right? Whereas the insoluble ones have a chance, like they're probably covalent. So I can say from this that probably it's either A that's going to be the answer or D that's going to be the answer, because those are the two that are insoluble in aqueous solution, so they're not ionic, and you want giant covalent, so obviously it has to be not ionic. But then I already cancelled out A because of, you know, the very low melting and boiling points, because obviously a giant covalent structure would have quite a high melting and quite a high boiling point as well, right? So melting point and boiling point, okay. But therefore that means that I have cancelled out option A and B and C, and the only candidate that's left is then D. And yes, it does make sense that, you know, obviously giant covalent structure would have poor electrical conductivity solid but poor electrical conductivity of liquid. I guess you could also cancel it from that sense that C cannot be the answer either, because, you know, it says good electrical conductivity of liquid. But anyways, the point being that D is your answer. So high melting point, high boiling point, but insoluble aqueous solution because it's not ionic. It's giant covalent, right? Maria. Okay, that's the answer. D. Okay. Next question. A student mixed 25 cubic centimeters of 0.350 mole per cubic decimeter sodium hydroxide solution with 25 cubic centimeters of 0.350 mole per cubic decimeter hydrochloric acid. The temperature rose by 2.50 degrees Celsius. Assume that no heat was lost to the surroundings. Okay. Then the final mixture had a specific heat capacity of 4.020 joule per cubic centimeter per Kelvin. What is the molar enthalpy change for the reaction? Okay, so we know, let's see what we know. We know that delta H equals to MC delta T, right? And then, you know, the temperature rose by 2.50 degrees Celsius, which means it's an exothermic reaction, right? And therefore I can make it kind of like minus MC delta T, because, you know, exothermic because temperature rising, so heat is given off to the surroundings. So I have to put a minus sign for the enthalpy change. And now I'll just substitute stuff inside this. So minus, and let me think. I mean, you know that formula, m equals to rho v, right? So basically, because it's you assume the density is that of water, like that's one of the assumptions you make while using this equation. So if I take it as 1 cubic gram per cubic centimeter times volume equals to m, that implies that my mass equals to my volume, right? I mean, this is an assumption we're making, of course, because, you know, I have hydrochloric acid and sodium hydroxide, so technically you would say, like, why would I consider the density of water then? But you do. That just makes your life easy. And so I have m equals to v, all right? So basically, whatever my volume is, that is equal to my mass in grams. So whatever my volume in cubic centimeters is, then that is equivalent to my mass in grams. Or like, I mean, if you want to think about it in kilograms per cubic meter, then equivalently you have, well, I mean, then you would have a factor of, then it would be m equals to 1,000 times v. That's a different scenario. But anyways, this statement that I've made here is true, considering the density to be 1 gram per cubic centimeter. Okay, so that means that my value of m here is going to be what? Well, I have 25 cubic centimeters of sodium hydroxide solution and 25 cubic centimeters of hydrochloric acid. So obviously 25 plus 25 is 50 cubic centimeters, right? So therefore, my volume and my mass are equal, right? So then my mass is going to be, if my volume is 50.0 cubic centimeters, I should stop circling things, it makes it so messy. But anyways, if my volume is that much, then my mass is also going to be 50.0 grams, okay? Times my C, my specific heat capacity here is 4.20 joules per cubic centimeter per Kelvin. And do I need to convert anything to, well, let me think about this. I mean, do I really need to convert things to SI units? I mean, I could, like, again, because my mass is equivalent to my volume, then it doesn't matter if I use mass units here or volume units. So I could, instead of 50.0 grams, I could write 50.0 cubic centimeters. And why am I going to do that? Because I have 4.020 joules per cubic centimeter per Kelvin as my specific heat capacity, right? So per cubic centimeter, you can write it as joule per gram per Kelvin, of course, but joule per cubic centimeter per Kelvin is also fine. So then we have C, so this is my specific heat capacity, if I did not mention that before. But yeah, 4.20 joule per cubic centimeter per Kelvin. I'm writing it like this. On the other hand, you could also just write gram, and then you could write this as joule per gram per Kelvin, as long as your dimensional analysis is correct and stuff, right? Anyways, you multiply this by your temperature then, which is 2.50 degrees Celsius. Now it's temperature rise, right? So it doesn't matter if it's in degrees Celsius or in Kelvin, because that will be the same. Because degrees Celsius plus 273.15 is equivalent to Kelvin, right? The temperature in Kelvin. So yeah, the temperature rise, like 2.50 degrees Celsius is equal to 2.50 Kelvin temperature rise, right? I mean, like delta T. Like obviously T will be different in Kelvin, but then delta T is the same. So I will write this as 2.50 kelvins, and then they have stated things in kilojoules per mole. So it might be smart. Well, first let me see what cancels. This cancels obviously. My per cal K minus 1 and K, they both cancel, and then I just have joules left over, but I want it to become kilojoules, so I will divide by 1,000 firstly to make this conversion. Okay, so divide by 1,000, and then it becomes joules in 1 kilojoule. I mean, you don't need to write this, I suppose, but it just makes it easier for me to understand that, oh, this is canceling with this, and then you get kilojoules as your unit. And what else do I have to do? Well, I also have to make it kilojoules per mole, right? So let me multiply by mole in the denominator, which is the same as having per mole. But which moles should I use? Well, I should use the moles of the limiting factor, of course, right? So let me find the limiting factor. So firstly, for sodium hydroxide, I have 25.0 cubic centimeters and 0.350 mole per cubic decimeter. Please remember the formula is N equals to CV, right? So moles equals concentration times volume. So then my concentration then is 0.350 mole per cubic decimeter. And then my times the volume, so that's 25.0 cubic centimeters, and I want to make that into cubic decimeters. So if I'm not wrong about my unit conversion, then I multiply by 10 to the power of minus 3. So I divide by 1,000 basically to convert from cubic centimeters to cubic decimeters. 0.350 into I should turn on the light because I can't see anything. Wait a second, guys. Came back. So I will just use my calculator, as should you all. But I get my moles for NaOH as, write this down, 0.00875 moles. All right, let me do the same thing for my hydrochloric acid. So I can write over here NaOH, right? So moles of NaOH, and then I can write NHCl. So that's going to be point 0.350. Oh, actually, it's the same, isn't it? It is the same. That's 25 cubic centimeters of 0.350 mole per cubic decimeter of hydroxide and 25.0 cubic decimeters of 0.350 moles per cubic decimeter hydrochloric acid. And the good thing is that if you think about the equation, then NaOH plus HCl gives you NaCl plus H2, so it's 1-to-1 ratio between them. So it doesn't really matter which moles we consider because both of them are 0.00875. So I don't know why I even went down this rabbit hole, but it's good that we at least calculated it for one of them. But anyways, that means that the moles that we will use in the denominator are going to be 0.00875 moles simply, which is equivalent for sodium hydroxide and for HCl. Okay, so now let us use our calculators again and calculate this out. 0.20 into 2.50 over 1000 into 0.00875. Okay, so we get minus, should I make an arrow or something? But yes, minus 60.0 kilojoules per mole. All right, so that's the answer I get, and that is B. So then B must be my answer, unless you guys write in the comments it is not. Then we'll figure it out. But yeah, B should be the answer. Okay, next question. AlCl3 vapor forms molecules with formula Al2Cl6 as it is cooled. What happens to the bond angles during the change from AlCl3 to Al2Cl6? Well, there are a lot of options. I mean, of course, there are 4 options. It's MCQs, well, MCQs at least. But let me just draw out the molecules. So Al, Cl, Cl, Cl. This is AlCl3. Aluminium, it is in group 3, right? So it has 3 electrons in its valence shell. Anyways, so that means, yeah, that's just how it is. And then that's how it looks. These are electron pairs, by the way. I mean, you could draw it like this as well, but university habit that I've gotten into is this lines for electron pairs. So yeah, anyways, what was I going to do? Yeah, I was going to find the bond angle. So so it's 1. So how many sigma bonds are there connecting to Al and how many lone pairs around this? So I'm trying to find the steric number, obviously, around the central atom aluminium. So I have 1 sigma bond, 2 sigma bond, 3 sigma bonds. I have 3 sigma bonds and 0 lone pairs. So 3 plus 0, that gives me a steric number of 3, which implies that, it has sp2 hybridization. And since there are no lone pairs, so I can assume that, okay, yeah, so it's sp2 and it is trigonal planar. That is the shape. And then what is the bond angle for trigonal planar? It is 120 degrees, right? So that means AlCl3 has bond angles. These bond angles are 120 degrees, 120 degrees, 120 degrees. All right. And then I'll look at Al2Cl6, which is annoying to draw sometimes, but we will draw it nevertheless. AlCl, Cl, Cl, and do I remember how to draw this? Hopefully, but basically, should be a lone pair. I mean, drawn. Nah, never mind. What I do is, yeah, okay, so one like that, and then one that's just lone pair being transferred, kind of, and yeah. Don't know if I should show the lone pair that's being transferred or not, but it is quite um obvious, is it not, that there's a lone pair being transferred? I mean, obviously there's an arrow going like this, and it's an arrow, so obviously you can tell that there are 2 electrons being donated. So do I really need to draw the lone pair? I don't think so, right? I don't think we need to do that for the Lewis structure, but anyways, this is how it is, and let us count the. So they did say the bond angles during the change from air to, yeah, so then I should, obviously the central atom is still, it looks aluminium, right? So I will take, for example, this aluminium atom, just because, I don't know, I feel like it. I mean, the other aluminium atom will be equivalent, but anyways, I will see the number of sigma bonds and number of lone pairs around this. So I have 1 sigma bond, 2 sigma bond, 3 sigma bond, 4 sigma bonds. So I have 4 sigma bonds and I have 0 lone pairs. So 4 plus 0 is going to give me a steric number of 4, which implies that it has sp3 hybridization. And since there are no lone pairs, so sp3 hybridization points to tetrahedral geometry in this case, and tetrahedral geometry of course implies bond angles of 109.5 degrees. So this is 109.5 degrees, this is 109.5 degrees, this is 109.5 degrees. Why is this so fun? This is 109.5 degrees. Actually, I guess I just like repetitive tasks sometimes, which anyways. Same for the other aluminium atom. But yeah, okay, so the change from bond angle when you're going from AlCl3 to Al2Cl6 is 120 degrees to 109.5 degree, which means that your bond angle decreases, right? So if I look at the options now, I see some decrease, others remain the same. Some decrease, some remain the same. Some increase, some remain the same. They all decrease, they all increase. So I would say they all decrease seems like a plausible answer. You know. So yeah, I'm going to say that 6. The answer for question number 6 is C, and then we go to the next question. The contact process is used in the manufacture of sulfuric acid. The equation for the main reaction is shown. Which statement about this reaction is incorrect? So, first statement is increased pressure gives a higher yield of SO3. Well, would it? Well, if I have pressure increasing, then like pressure increasing in the reaction mixture in general, I mean, pressure increase means that you have a greater pressure, you have to reduce that somehow. And how do you reduce pressure? By reducing the number of moles in the reaction mixture. So basically I have 3 moles of gas on the left hand side, whereas on the right hand side I only have 2 moles of gas. So if my pressure increases, then how do I oppose that change, or how does the reaction mixture oppose that change? I don't do it, the reaction mixture does it. But anyways, pressure increases, that implies that your number of moles have to decrease, right? And how do you decrease the number of moles? By shifting the equilibrium from the left hand side to the right hand side, so that it goes more from 3 moles to 2 moles. So I mean the 2 moles side is preferred because that's less moles of gas, and therefore your pressure will decrease if you have less number of moles, right? So that means that increased pressure does indeed give a higher yield of SO3 because your reaction mixture, your equilibrium will favor the right hand side, the forward reaction more, to decrease the number of moles and thus decrease the pressure and thus restore equilibrium according to Le Chatelier's principle, right? So A is correct, but we want an incorrect statement, so that means A cannot be our answer. And so we go to the next question. Increased temperature gives a higher yield of SO3. Well, I can see delta H is written over here, which is minus 196 kilojoules per mole. What does that mean? That means that the forward reaction is exothermic, obviously, because there's a minus sign for delta H, and then backward reaction is endothermic, right? And so if I increase the temperature, which of the reactions will be favored? I'm pretty sure. I mean, it's kind of, kind of instinctive maybe at this point, but increased temperature favors the endothermic reaction side, right? So it's going to favor the backward reaction, because increase in temperature basically, it favors the endothermic reaction, because endothermic reaction, it does not release energy, but rather it absorbs the energy, right? So if you favor the endothermic reaction, your extra temperature, like when you increase your temperature, then if you favor the endothermic reaction, then your temperature will be decreased because that energy will be absorbed by the reaction mixture. And so when your temperature decreases, then obviously that's a way to restore the equilibrium back again by Le Chatelier's principle, right? So that's why the endothermic reaction side is favored, so the backward reaction is favored with increased temperature. I realize I'm talking too fast. Some of you guys have commented in my previous videos that I talk too fast. I get excited sometimes, okay? I'll try to talk a bit slower, but yeah, that happens. And so that means that increased temperature, if it favors the backward reaction, then you get a lower yield of SO3 because it's going, you're breaking down the SO3 back into SO2 and O2, right? So that means that, well, B seems to be incorrect then. So I'm going to say B is my answer, but we will also check options C and D. So let us do that. In the forward reaction, the oxidation state of sulfur changes from +4 to +6. Let me check. So oxygen, it usually has a fixed oxidation state of -2, right? And if we have SO2, then I have, just for balance, I can say -2, and then because, SO2 overall, it has no, like, it's a compound that's, not charged, so it has zero oxidation state overall, right? So that means -2, and then I have to multiply this by 2 because I have two oxygen atoms, and then plus, I do not know the oxidation state of sulfur. I'm finding it, so I'm going to keep it as x. And there's only one sulfur atom, so I can say x times 1. And this equals to 0 because you have overall no charge in SO2. So then x minus 4 plus x equals to 0. And so x equals to +4 implies that my sulfur oxidation state here is +4, right? So sulfur here is +4. So that part is correct here. As for SO3, I do the same procedure. So I have -2 times, well, now I have 3 oxygen atoms, it will be times 3, plus, again, I'm keeping sulfur as x, and then there's only one sulfur atom, so I'm keeping it as times 1 equals to 0, because there's no overall charge in SO3, and so no overall oxidation state, yeah. And x minus 6 plus x equals to 0, and so x equals to +6, right? So that is +6. Sulfur is +6 here, then that statement is also right. So in the forward reaction, the oxidation state of sulfur indeed changes from +4 to +6. So this is a correct statement, which means it's not the one we want because we want an incorrect statement. Let's look at the last option. Vanadium 5 oxide is used as a catalyst. It is indeed used as a catalyst in the contact process. So that's just like, a thing you should know, I guess. But yeah, that is definitely correct. So I'm going to put a tick mark there as well. So the only option that's incorrect then is B. So it must be the answer. Okay. Now let's go to the next question. When making sparkler fireworks, a mixture of barium nitrate powder with aluminium powder, water, and glue is coated onto wires and allowed to dry. At this stage, the following exothermic reaction may occur. So this is the reaction. And which conditions would be the best to reduce the rate of this reaction during the drying process and would also keep the aluminium and barium nitrate unchanged? Okay, so this reaction is exothermic in the forward direction and obviously endo in the backward direction, but then they haven't really written that reversible arrow. But anyways, exothermic in the forward direction, the direction anyways. Okay, so it's an exothermic reaction. Let's say that is definitely a true statement. I don't know if it's reversible or not, but anyways. Uh, so obviously exothermic reaction, you want to keep the aluminium and barium nitrate unchanged, right? Which means you want the left hand side of the reaction to be favored, is it? Um, but you also want the rate of the reaction to be reduced. Hmm. 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 Well, hmm. So I mean, barium hydroxide is basic, strongly basic. Ammonia is basic, right? ALOH thrice, aluminum hydroxide, that is amphoteric, and water. Water is obviously neutral. Barium nitrate, it's formed from neutralization reaction. I don't know. I mean, maybe it would be around neutral at least, even if it's not perfectly neutral, but yeah. And aluminium, well, I mean, metals are usually basic, right? Point being, anyways, that if I have a pH of 14 or so, that would probably not be good, right? Because there would be reactions and stuff, I think, with like ALOH thrice reacting. and stuff like that. I mean, in general, it might be better to keep the pH as 7, I would say. Maybe I should use the logic that, well, what will you want the aluminium and barium nitrate unchanged? If I look at it from the perspective of aluminium and barium nitrate, well, yeah, I mean, aluminium, I wouldn't want it to react, right? So, I mean, it's much more likely to react at like 14 pH, or maybe even at low pH, very low pH, but then 7 is neutral, so it wouldn't really react. So then it's if you want them to be unchanged, because I guess this is kind of like forward directions. I mean, I should just think about the reactants really, right? Not the products. So never mind. But then yeah, pH 7 would be the best. And as for barium nitrate, yeah, again, I mean, pH 7 would be better. Otherwise, who knows? It might react, or maybe. Hmm. Yeah, I mean, I guess you would have more of barium hydroxide if it's higher higher pH of the reaction. I mean, does that make sense? Because I mean, it does make sense in this in the sense that your barium hydroxide is basic, so it's going to be more present. Like that form of barium ion will be present more. Barium salt will be present more if you are at a higher pH, I guess. But then you don't really think about Le Chateliers when you're thinking about pH, right? So I guess it does make sense that like if you're at a higher pH, then you have more of barium hydroxide, I guess. Um, yeah. I mean, if my logic is not right, you guys can tell me. Anyways, so we're done with this part. Like, would also keep the aluminum and barium nitrate unchanged. I'm pretty sure, like, pH 7. Maybe that also just makes intuitive sense, I guess. I don't know. Maybe we don't need to think about it that much. But anyways, what would be the best to reduce the rate of this reaction? Now that's an important thing because they're not actually asking you about, because you have a lower temperature and you have a higher temperature. Hope my writing is understandable, but lower temperature and higher temperature. Now, because it's an exothermic reaction, you would think about that, but actually they're not asking you about the yield. They're asking you about the rate of the reaction, so that's much simpler. Like you just think about kinetics, right? And um, um, yeah. So I mean, how would it reduce the rate of the reaction? By using a lower temperature, right? So they're not asking you about like the thermodynamics and all that, but just about the kinetics. And so like yeah, lower temperature should be the one that favors, well, not favors nothing, but like you decrease the rate of the reaction, and so you have less of this reaction occurring in general. So I would say either A or B is the answer in that case because it's 298 kelvins, which is a lower temperature, but then we also have pH 7, so that makes A or C the answer, which means that A must be the answer because that's the one that has two ticks. All right. So yeah, A is the answer, and um, yeah, I mean, if you guys have better explanations for this, maybe you can write it in the comment section. Thank you. Okay, next question. Okay, let's look which molecular structure will have the smallest overall type. I'll just make this a bit bigger. Okay, so I mean, at least this is how organic chemists draw the arrows. Okay, so never mind the accuracy, but I think yeah, like in quantum physics people, I think they try it in the opposite way. But anyways, this is partial positive, this is partial negative. Okay, I'm assuming this is a plus kind of symbol. So yeah, anyways, that's one dipole, CH, and I don't think that has a very big dipole moment. I mean, maybe the data booklet has a table for the electronegativity values, so Pauling electronegativity values. I'm not sure if this one does, but I don't really need it right now, anyways. But yeah, that's one dipole moment. Then I also have a CH2Cl, right? So I mean, I can draw it out kind of maybe a bit better. But CH, and then this is a double bond as well. So this is partial positive, partial negative. So I have another dipole here, kind of. And yeah, C will obviously not have a really a dipole moment, and CH I'm assuming is a negligible dipole moment as well. Then CCl is also polar bonds again here, and here I have dipole moments. CCH3, CCH3, those are not going to have very significant dipoles. And here CCl again, I have a dipole moment. Here CCl, I also have another dipole moment. And then in this molecule, yeah, again I have CCl as the polar bond. This is a polar bond. I'm not considering CC bond, although obviously that'll have zero because we're the same atom. So I'm not considering as CH again. I'm assuming it's negligible dipole moment. But anyways, those are the dipole moments I can see, and let us now kind of resolve our components. So use a different color maybe. That might be clearer. But here I have this going like this, and this going like this going like this going like. I'm just resolving my forces. So, I mean, my overall dipole moment then is in this direction basically. Maybe that's not the best way to draw it. Maybe I use another color then as well. But at first I'll draw all of them. I'll resolve all of them, and then I'll finally draw the final things. All right, how about that? And yeah, this one can be resolved as this and like that. And yeah, this one on the other hand, I will use the triangle method for maybe. Wait. Would that be right? I mean, I feel that, basically, this is CCl, and this CCl bond I feel is more, has a greater electronegativity difference because you also have a double bond here, right? So that's a region of high electronegativity. Whereas this other CH2Cl, where I have a dipole moment, that's this carbon is attached to this carbon, which is just a single bond as opposed to a double bond, so it's less electronegativity region in that sense. I feel like this would be a smaller arrow, whereas that will be a larger arrow. So overall, I don't know if I'm kind of making sense, but overall, then your dipole moment will be kind of teetering more towards, or am I wrong? No, sometimes maybe I am wrong. Let me think about this. Maybe it's the opposite thing actually, because this is partial positive, right? So it'll be less partial positive because it's near to a region of high electronegativity then, right? Somewhat. So then you would have a smaller arrow there, but a larger arrow here, maybe. And then your overall resolved arrow would be going in that direction, maybe. Maybe. And so you can kind of say that my overall dipole is in that direction. Maybe I should use a different color. My overall dipole is in that direction. I'm just assuming, by the way, maybe my logic is not right. Let me think. Could it be that it's more partial positive? I mean, it is possible. On the other hand, hmm, I don't know actually. I feel like maybe there might be a less electronegativity difference because this is a region of high electron density, and then you have partial negativity, but this one is partial positive, and then because of the region of high electron density, there's less difference between the C and Cl, so it's a smaller dipole for this CCl bond, right? And so then you should have a smaller arrow there, a larger arrow for the CH2Cl. This CCl bond should have a larger arrow, I think. And then your resolve, like your final arrow should be to kind of in this direction, right? That's what I think, but maybe I'm wrong. Anyways, you guys can comment that in the comment section. But anyways, that's the arrow that I'm getting, and then in this direction I would have the arrow here, right? And then because those two cancel out, of course, up and down, right? Well, I mean, at least partially cancel out, but I think they are quite equivalent. Equivalent because you have CCH3 here, CCH3, so it's kind of, yeah, equivalent in up and down molecule, right? So yeah, and then as for option C, these two I would say seem to cancel out, but then you have these two, so the overall dipole moment would be upwards, kind of, or not upwards, but like, I'm just resolving my dipoles, kind of. Anyways, and as for this one, up cancels out the down and the left cancels out the right, so I have no overall dipole moment. And so since they're asking for which molecular structure will have the smallest overall dipole, I suppose so tangent about A didn't even really matter, I guess. But then the answer is going to be D, because the D is quite close to 0, right? So yeah, the two dipoles are effectively canceling each other out here. Anyways, let us go to question number 10. The equilibrium constant Kc for the reaction H2 gaseous plus I2 gaseous gives 2HI gaseous is 60 at 450 degrees Celsius. What is the number of moles of hydrogen iodide in equilibrium with 2 moles of hydrogen and 0.3 moles of iodine at 450 degrees Celsius? So okay, so I know that we have 2 moles of hydrogen, and I also know that we have 0.3 moles of iodine. On the other hand, I do not know how much HI I have, so I'm going to take that as X at 450 degrees Celsius. Now, assuming that I have the same volume, honestly, it doesn't matter. I mean, okay, so I'm taking the moles, and then you have to realize that concentration equals to N by V, right? So I mean, if I'm taking my constant, the equilibrium constant Kc, that's going to be 2 moles divided by the whatever arbitrary volume I have. Actually, no, I should make it products over the reactants, right? So then I have HI in the numerator, so I have X X over the whatever arbitrary volume I have squared divided by H2. So that's 2 moles over whatever arbitrary I have volume I have times 0.3 for I2 over whatever arbitrary volume I have. Arbitrary means random. Like, I don't know, some random number, because I didn't mention it. And the reason they didn't mention it because I have 2 moles on the left hand side, 2 moles on the right hand side, so it cancels out and stuff of gas. And so my V squared cancels out my V squared in the bottom as well. So that's why. Okay, so this is equivalent to then x squared over 2 into 0.3 basically. And this is equal to Kc, which is given, the value is given as 60. Alright, so then I find out that x equals to root of 60 into 2 into 0.3. And so what is this? That is 6. So this is 6. The answer is 6 moles. 6 moles. Alright, so C is going to be the answer. Yeah, basically. Now let's go to the next question. Boltzmann distributions are shown in the diagrams. In diagram 1, one curve, P or Q, corresponds to a temperature higher than that of the other curve. In diagram 2, one line, X or Y, corresponds to the activation energy in the presence of a catalyst, and the other line corresponds to the activation energy of the same reaction in the absence of a catalyst. Which combination gives the correct curve and line? Alright, so I'll do diagram 2 first. Or maybe I'll do diagram 1 first, but does it really matter? The higher temperature is going to be Q, and the presence of catalyst is going to be, I believe it is going to be X. Well, okay, now I'll explain it as well. But Boltzmann curve, the peak becomes, as the temperature increases, the peak becomes flatter, so it's not as pointy, and it becomes flatter, and it also shifts to the right and becomes lower. What happened? What is happening? Okay, that's kind of a sad mistake, but anyways. So Q has to represent the higher temperature, because basically what happens is that more of your molecules are at a higher molecular energy at a higher temperature. So like basically it shifts right. So that means that there's more molecules that have a higher molecular energy because your peak has shifted to the right. So before at P, my peak was more to the left. So most of my molecules you can see were at a lower molecular energy, but now when my temperature increases, more of my molecules are at a higher molecular energy, right? And yeah, that's one thing. And also the fact that there are more molecules to the right of the peak, whereas at P there are less molecules right of the peak, because as you can, what I mean to say is that the peak is lower basically. So there's the probability of having the molecules having this highest, sorry, this peak energy is less, and there are more molecules have a higher molecular energy. I mean, well, not more molecules having a higher molecular energy because it is a peak for a reason, right? It's the highest number of molecules have this energy, but you get my point, right? Like everything shifts to the right basically. So that's what happens when you have a higher temperature. So Q has to be the one that's higher temperature. Okay. Okay. And as for diagram two, the catalyst thing. So X is the one that is in the presence of a catalyst, and why is that? It's because in the presence of a catalyst, you basically have more molecules that have an energy greater than or equal to the activation energy. So initially, for example, if Y was my activation energy, and then I had this many molecules that were to the right of the line Y, right? But then now, like after I use a catalyst, like basically my curve obviously stays the same, but then what happens is that um I have more molecules that have, like, my activation energy lowers, right? So using a catalyst, so then I have more molecules that are to the right of that activation energy. So see this whole yellow region, that you get, so my activation energy has lowered. So this is my new activation energy with a catalyst, right? That's why, so X has to be in the presence of a catalyst. I hope that makes sense. And so my answer is going to be C. Okay. So yeah, and now we can go to question number 12. Redox reactions occur very frequently in the chemistry of group 7. Which statement is correct? Chlorine will oxidize bromide ions but not iodide ions. Fluorine is the weakest oxidizing agent out of F2Cl2 Br2 and I2. Iodide ions are the weakest reducing agent out of F minus Cl minus Br minus and I minus. When chlorine reacts with water, chlorine is both oxidized and reduced. Well, I mean, I can write it down. Fluorine, chlorine, bromine, iodine, aspartame. Nobody actually thinks about aspartame sadly, but anyways, F minus, Cl minus, Br minus, I minus, At minus. Okay. And as you can see, okay, so this column, I have my oxidation number is 0 because they're the elemental forms, right? So F2Cl2, Br2, how they exist in nature. Then F minus, Cl minus, Br minus, I minus, At minus, you can see the oxidation states are actually -1 because, this the charge on the ion as well. So yeah, -1. So that means if I'm going from 0 to -1, that is reduction, right? Because you're losing electron, you're gaining an electron. I'm so mistaken, but anyways, you're gaining an electron. And so if that is reduction, that implies that they are oxidizing agents, right? So that means basically what I'm trying to say, I'm just trying to give you logic or reasoning because I always forget, honestly, that the left hand side ones are the oxidizing agents, whereas the right hand side ones are, why am I so bad at drawing today? Whereas the right hand side ones are reducing agents because the left hand side ones are being reduced to form the right hand side ones. So then they must be oxidizing agents. These are oxidizing agents, whereas the right hand side ones are the reducing agents. Alright, so now I will see the options again. So chlorine will oxidize bromide ions. Does it make sense? Yeah, it could be an oxidizer. I'm just looking at these words. Fluorine is the weakest oxidizing agent. Okay, again, this is an oxidizing agent, so I'm going to keep that. It's not a wrong statement. Iodide ions, again, that's a correct statement. Reducing agent. I mean, in that sense, when chlorine reacts with water, chlorine is both oxidized and reduced. Okay, so I can right now cannot cancel out any options just through my original logic. But then chlorine will oxidize bromide ions, but not iodide ions. So what you should know is that down this group, um, what happens is that they become weaker oxidizing agents. Like in general, like group 7, like when you go down it, your reactivity decreases, right? So the ion, so the atom, like the chlorine atom is bigger, and so it's just less, like Cl2 is less reactive in a way. So yeah, weaker oxidizing agents like that Cl bond is also, yeah. Um, yeah, basically they become weaker oxidizing agents down the group. Whereas on the other side, if you look at F minus Cl minus Br minus I minus Ag minus, they become stronger reducing agents. Because again, reduction is gain. So if they're reducing agents, they are themselves being oxidized, so they lose electrons, right, during the reactions. And so if they lose electrons, it's easier to lose electron from a bigger atom. And obviously I minus is, for example, much bigger than Br minus, and therefore I minus is a better reducing agent. And these have opposing trends. I mean, if those are stronger reducing agents, then this will be weaker oxidizing agents. Okay, because it's harder for them, because oxidizing agents means they're being reduced themselves, and it's harder to be reduced, harder to gain electrons when you are a bigger atom or bigger molecule, I suppose. But yeah, you get the point. And therefore, if I look at the options now, chlorine will oxidize bromide ions but not iodide ions. But chlorine is a stronger oxidizing agent than both bromine and iodine. But I mean, I could find you looking at the chlorine will oxidize bromide or iodide, of course, not bromine or iodine, but bromide or iodide. But but then it can oxidize both bromide and iodide, I would say. So this is wrong. It can oxidize both of them. So A is not right. Fluorine is the biggest oxidizing agent out of fluorine, chlorine, bromine, iodine. No, it is the strongest, in fact. This is wrong as well. Iodide ions are the weakest reducing agent out of fluoride, chloride, bromide, and iodide. No, they're the strongest out of these four, so that's wrong as well. So that leaves only option D. When chlorine reacts with water, chlorine is both oxidized and reduced. So, I mean, I would say that's right, because chlorine in general, it seems to be a very much of an that substance that is, oxidized and reduced simultaneously. But let me just write an equation. Chlorine plus water, giving you, I don't know, HCl plus HClO makes sense to me, yeah. And so, like, if you think about it, would this be a disproportionation reaction, like this chlorine being simultaneously oxidized and reduced? Well, this is zero. And in HCl, well, hydrogen usually has a fixed oxidation state of +1. So if this is +1, then since HCl overall is having an oxidation state of 0, so chlorine must here be -1. So okay, so this is 0 to -1. That is reduction, okay, of the chlorine. And then if I look at HCl, well, hydrogen usually has an fixed oxidation state of +1, whereas oxygen usually has a fixed oxidation state of -2. And then you have +1, -2, and let me say chlorine is X, so plus X equals to 0, because again HCl overall has 0 oxidation state. So then -1 plus X equals to 0, which implies X equals to +1. So chlorine here is +1. So if you're going from 0 to +1, that is in fact oxidation. So yes, 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 I am having simultaneous reduction and oxidation of chlorine. So it is definitely a disproportionate reaction, and so D is correct. Okay, so yeah, that means that yeah, D is right. Anyways, next question. When equal volumes of saturated solutions of barium hydroxide and calcium hydroxide are mixed, a white precipitate Y forms. Mixture is filtered and carbon dioxide is bubbled through the filtrate, producing a second white precipitate Z. So what are Y and Z? Okay, so I have barium hydroxide and calcium hydroxide, and I am mixing them, and you get a white precipitate Y forming. Well, what I do know, and the logic of this is more A2, so I'm not discussing it here, but then basically your metal sulfates for your group 2, like group 2 sulfates solubility decreases down the group, whereas group 2 sulfates, sorry, hydroxides, I should say, sorry. I don't know why I keep saying sulfates, okay. Hydroxide solubility increases down the group, okay, that's more E2 logic. Not AS logic, so I'm not explaining it here, but you should know this, you should definitely know this. And Therefore, if I have my group 2 like B Muira Ka Bada, okay, but if I have barium versus calcium, if I have the hydroxide, I would say that barium is definitely a more soluble salt. Like barium hydroxide is definitely a more soluble salt as compared to calcium hydroxide. So if this thing a white precipitate Y forms, it's more likely to be a calcium hydroxide precipitate, right? So I'm going to say it's either C or D. That's the answer because Y has to be either C or D, like calcium hydroxide or calcium hydroxide. No, I'm saying this, but okay. The mixture is filtered and carbon dioxide is bubbled through the filtrate, producing a second white precipitate Z. So this time, the mixture is filtered, right? And carbon dioxide is bubbled to the filtrate. Now, filtrate contains basically barium hydroxide then. And I get a second white precipitate when carbon dioxide is bubbled through it. So that means that BaOH plus CO2 is giving me BaCO3 as the precipitate, right? So BaCO3 has to be the answer. So if I am looking at these options, well, I can't have it as calcium hydroxide or barium hydroxide because I have to include carbon dioxide somewhere. And CaCO3 versus BaCO3, it's not CaCO3 because I filtered it and then I'm taking the filtrate, right? Not the residue. So then my answer is going to be BaCO3 for Z. And so my answer is going to be C because it's Y is calcium hydroxide and Z is barium carbonate. Alright? So C is going to be the answer. Okay, now next question. What is the order of increasing melting point of the four liquids shown? They're all, sorry, did I say liquids? Or the four chlorides shown? I don't know why I said liquids, but anyways, maybe I should think about states. Okay, and matter. But CCl4, that is a liquid at room temperature, I think. Whereas HCl, I mean, I'm considering hydrogen chloride rather than the hydrochloric acid. So hydrogen chloride is a gas at room temperature, I think. And MgCl2 is going to be a solid. PCl5, on the other hand, I am not sure. PCl3 is a solid, I think. I'm not check. PCl5 melting. And is it cheating to check it on Google? Melting point 160.5 degrees Celsius. Is PCl5 solid liquid then maybe? Liquid liquid no, it's not. Phosphorus pentachloride exists in equilibrium with 6 elements that are liquid at room temperature. Is PCl5 PCl3 is a liquid at room temperature, okay. Whereas PCl5 is a white solid which sublimes at 163 degrees Celsius. Sublimes, okay. That's interesting, but it's a solid. I mean, I saw that from the melting point, I suppose. It's obvious. But yeah, so PCl5 is the one that's solid, whereas PCl3 is the one that's liquid at room temperature, respectively. But yeah, okay, that's interesting information. I think it's is it colorless or so? But yeah, basically, so they talked about PCl5, so that would be a solid at room temperature. Anyways, why am I doing this? It's because it makes life easier, I suppose. I honestly don't know. But the lowest melting point will be for, well, HCl because it's gas at room temperature. I mean, that's just, I don't know, using your chemical intuition that you have built over the years, basically. CCl4, on the other hand, is a liquid at room temperature. And then if I compare MgCl2 and PCl5, well, PCl5 is a simple covalent structure, or at least more covalent than MgCl2. I mean, yeah, P and Cl are both non-metals. So then yeah, it is covalent, right? Simple covalent. And MgCl2 on the other hand is slightly ionic and therefore likely ionic. So then it's going to be having a much higher melting point as compared to PCl5, right? Even though both are solid at room temperature. So that's why the highest melting point is going to be for MgCl2. So the only option that makes sense to me, considering all that I know, is B. Okay? And all that I googled. But yeah. Now, when calcium is burnt in oxygen, what color is the flame? This is something that you should just know. I don't know what shade of red it is. I don't know if it's orange red or brick red or whatever, but it's red. Just know the flame tests, guys. Just know the flame tests. Okay, so yeah. Or it might be orange, I don't know, but you get the point. It's that color. Red. Red. It is red, isn't it? Just don't know the shade of red. I don't know. Which description of the bonding and acid-base nature of aluminium oxide is correct? I feel like this was mentioned in a question some time ago as well. Maybe it was at some question somewhere. I don't even know where it is now. But this one, question 8, yeah, there was aluminum hydroxide, wasn't it? This is similar. Okay, it's aluminum oxide. But anyways, it is amphoteric and not basic. And is it covalent or ionic? Well, it is ionic with some covalent character, I think, but mainly ionic, right? So because you have Al 2O3 or whatever, so you have non-metal and metal, so it's mainly ionic, but I think it has some covalent character. But yeah, so you have two ticks at C, so C is going to be your answer. I mean, yeah, in organic chemistry, it's a lot of just chemical intuition and patterns and knowing stuff. So just know the stuff, guys. Know the stuff. Question 17. Group 2 nitrates undergo thermal decomposition according to the following equation. XNO3 twice gives you XO plus 2NO2 plus half O2. Which group 2 nitrate requires the highest temperature to bring about its thermal decomposition? B. Mugira ka sar bada. Okay. Now, so this is group 2. So I need which one has the highest temperature for thermal decomposition. Down group 2, what happens is that, like, for example, I have, we should consider the ions, I suppose. Cat ions. And then I have NO3 minus on the other side, okay? Like, basically, 2 NO3 minus, technically, for each one, be NO3 twice and stuff like that, okay? But anyways, the point being that if I go down the group, my cation becomes larger, right? And since it becomes larger, it has a smaller charge density. Why does it have a smaller charge density? Um, the charge density is the charge over the size of the ion, and the charge, well, charge the same, but the size of the ion is increasing, which means the charge density decreases, right? I mean, that's kind of the definition of charge density. I mean, it's a density, right? So obviously, if you have a larger space, then your density is less, right? So if your ion is larger, then your charge density is less. Basically, so if your charge density decreases, then what that means is that your cation will distort your constant anion. Constant, I'm saying, because they're all nitrates, right? So your anion is constantly nitrate. So I mean, your cation, which is larger now, um, will distort your anion less. So there's less polarization of that anion, and because of that, your thermal decomposition is less easy because there's less distortion of the anion, so it's harder to, it's more, you have greater thermal stability, in other words. Greater, so you can write, I'll write this over here, so thermal stability increases down the group, right? As your charge density of the cation increases. And if your thermal stability increases, that's basically another way to say that your um, thermal decomposition kind of decreases, or basically for the same temperature. Or you could say, think of it as you need a higher temperature to bring about that thermal decomposition. Therefore, which group 2 nitrate requires the highest temperature to bring about its thermal decomposition? That's going to be the one that's much lower down the group. So if I'm comparing strontium, magnesium, calcium, barium. So magnesium, calcium, barium, strontium. Okay, so barium is the one that's lowest compared from magnesium, calcium, strontium, and barium. So I'm going to say the answer is A, barium nitrate. Okay. Now let's move to the next question. Use the data booklet is relevant to this question. A chemist took 2 cubic decimeters of nitrogen gas measured under room conditions and reacted it with a large volume of hydrogen gas in order to produce ammonia. Only 15% of the nitrogen gas reacted to produce ammonia. What mass of ammonia was formed? So I'm just going to write down the equation because it's fun to write down equations. Okay. And I know this is 2.00 cubic decimeters of nitrogen gas, a large volume of hydrogen gas, so I just say excess or so. And what else do I know? I know that hmm, I know that 15% of the nitrogen gas reacted to produce ammonia. So let me just it's under room conditions, right? So I can assume because under room conditions, 1 mole of a gas occupies 24.0 cubic decimeters, if I'm not mistaken. Did they mention that in the booklet, in the data booklet somewhere? They did, didn't they? They did. Here, see, molar volume of gas, Vm equals to 24.0 cubic decimeters per mole under room conditions. Under room conditions, because that is at standard temperature and pressure. Okay, so room conditions. This is 24.0 cubic decimeters, so I'm going to say N equals to V over 24. So then this is going to be 24. So this, like my volume is 2.00 cubic decimeters over 24.0 cubic decimeters per mole. Right, so what's going to be my moles of nitrogen? Basically, that's what I'm trying to find out right now. And 2. Okay, so that'll be 2 over 24, which is simply 1 over 12. I don't know if I should, um, you know, I'll just keep it as a fraction because fractions are cool and I am not scared of fractions. I'm not in grade 5 anymore. Okay, that's 0.08. I don't know when people learn fractions. When do people learn fractions? Grade 3? I don't know. 0.083 moles. Okay, and then only 15% of the nitrogen gas reacted to produce ammonia. So that means that how many? I'm erasing this for a while because it's kind of disrupting my beautiful, uh, well, columns. No, not actually columns. We have not drawn lines, but you can see, I'm writing the data for nitrogen, under nitrogen, hydrogen, under hydrogen, and so on. But if only 15% of nitrogen gas reacted, well, then I can say that actually how much of the nitrogen did I actually use 1 over 12 into 15 over 100, 15%, right? So that gives me point, well, I mean, 3, 4 to 12, 3, 5 to 15, so it's 5 over 4 into 100. So that's going to be anyways 0.0125 moles, all right? So that's that. And hydrogen I'm ignoring anyways because it's excess, but then how many moles of NH3 do I have in this case? Well, um, ammonia has, well, nitrogen has 14.0 gram per mole molar mass, and then hydrogen has 1.00, so then that's going to be a total molar mass of 17.0 grams per mole, right? So then if I want to find the moles, then N equals to M over MR. What am I doing? And am I doing this right even? I should be doing this right. Okay, so then I'm basically, since I am, this is 0.0125 moles that are being used, reacted to produce the ammonia. So that means that what is it? should I consider the change that is happening? Maybe. I think I should. So basically, what I will do is that how okay, so 1 over I have to consider the table because it's an ice table, right? I mean, I love ice tables. If you guys want to research more about them, just research. I think it might be in the textbooks as well. But basically the change here is 1/12 minus 0.0125, which is a change of 0.07083 moles. More accurately, it's 17 over 240 moles minus 17 over 240 moles. Wait a second. Hmm. Hmm. Is it that way? No, it's not. I'm so sorry. I am so sorry. But actually, I got this is 0.0125 moles, right? So that means that my change, because I said only 15% of the nitrogen gas reacted to produce ammonia. So that means that how many moles did I lose? I got minus 0.0125, right? Basically, this is the number that I have here. So these are the ones that are reacting. So that means over here I should have plus 0.0125 into 2. So because the stoichiometric ratio here is 1:2. So 1:2, right? So that's why I have to multiply by 2. So like that is being, I'm losing 0.0125 moles of nitrogen on that side, and I'm gaining 0.0125 into 2 moles of ammonia on this side. So 0.0125 into 2 is 0.025 moles of ammonia. Okay, and then I want to find the mass because that's what the question asks. So M equals to N times MR. So I make it 0.025 moles multiplied by 17.0 grams per mole. Okay, such a beautiful handwriting, I know. And you basically find this answer. It comes out to be 0.425 grams. All right. So I'll check the options now, and I do have 0.425 grams, which is great. So that should be my answer. Okay. Now let us go to the next question. Use of the data booklet is relevant to this question. Which graph correctly shows relative electronegativity plotted against relative atomic radius for the elements Na, Mg, Al, and Si? So I mean, it's period 3, right? So I'll just write down sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. I just like writing down period 3, honestly. Period 3 and group 2, those are two of my favorite things to write down. Anyways, so if I think about electronegativity, well, um, definitely. Hmm. I mean, I don't know if it's that simple, but basically, what happens is that your electronegativity increases across a period, right? Because your atomic radius is slightly decreasing across a period, like very slightly. I mean, I suppose I'm showing a much bigger change, but it's slightly decreasing because your number of shells remains the same, but then um your mass number is increasing, like your atomic number is increasing, right? So your number of protons is increasing, so you have a greater nuclear charge, and therefore that poses your electronegativity is increasing across a period, and then yeah, because your proton number increases while your shielding effect is basically the same, and yeah, electronegativity increases. Also, I'm really tired right now, so I mean, if I'm giving any wrong explanations, I would really appreciate if you guys write it down in the comments, okay? But basically, that should just be a trend like this upwards. Sodium is less than magnesium, which is less than aluminium, which is less than silicon. So silicon has the highest electronegativity, which makes sense. So across the period, your electronegativity increases, and so I'm going to kind of cancel out A already, cancel out C already, cancel out, well, D seems right till now, B seems right till now. Now we need to use our logic of relative atomic radius. And again, the atomic radius also, I think I mentioned this, but it also decreases across a period. So because again your shielding effect is pretty much the same, whereas because you have the same number of shells across the period, of course, and but your atomic number is increasing, right? So your the nuclear force of attraction on the valence electrons is increasing, and so then it's slightly smaller atomic radius as you go along the period. So therefore, silicon should have the smallest atomic radius, and but in D, it has the third smallest atomic radius for some reason, which doesn't make any sense if you're thinking across the period. So therefore, D has to be wrong, and so the only correct answer, or the only answer that's left over, is B, and so B must be the answer. And then we have organic questions, which I will do later. And so I'm taking a break, and I mean, I guess you can't tell in the video maybe because like the video is one continuous thing, but yeah, see you guys later. Okay. So many organic reactions need to be heated before reaction occurs, but some do not require heating. Which reaction occurs quickly at room temperature? Okay, so I can kind of immediately tell that it's the first reaction. C2H4 plus Br2 gives C2H4Br2 because that's the classic test for whether, a compound contains an alkene group, right? Because this is, a reaction that occurs at room temperature, right? This bromine water test, it's known as bromine water test. So yeah, it's definitely going to be A. As for B, yeah, I mean, you're adding water to your ethene molecule that requires heating or higher temperature, and also, yeah, again, eliminating water from ethanol to give you ethene also requires heating, and then substituting substitution reaction here, CH3 CH2OH plus HBr gives you CH3 CH2Br plus H2. That also requires heating. So all the other reactions do require heating. This one is a classic test for alkenes, and because it's a test, like, you would assume that your tests kind of need to be, well, sometimes easy, and yeah, this one is an easy test because it can be done at room temperature. So C2H4 plus Br2 gives you C2H4 Br2. The bromine water test is one that requires at room temperature. So yeah, it's just, you should know it from your chemical knowledge. Okay, so let's go to the next question now. Hydroxyethanol HOCH2CHO is heated under reflux with an excess of acidified potassium dichromate 6 until no further oxidation takes place. What is the skeletal formula of the organic product? Okay, so let me just draw it out. So I have, okay, they have skeletal formulas. So why don't I draw a skeletal structure as well? So I have two carbons, and then I have HOCH2CHO. So I have one alcohol group, and I also have one aldehyde group. So on this side, let me just draw my aldehyde group. You could draw the hydrogen if you want. I guess that's kind of common convention way of drawing it. I'm not sure. But anyways, the other side has your OH, okay? And so it is heated under reflux with an excess of acidified potassium dichromate until no further oxidation takes place. No further oxidation takes place. So I mean, when you oxidize this, well, I mean, but the aldehyde side, that obviously becomes the carboxylic acid, right? As for the alcohol side, I mean, you could say that initially it becomes aldehyde maybe, but then, until no further oxidation takes place, so that means you keep, it will just become the final product. So then aldehyde can then further be oxidized into, again, a carboxylic acid as well. So then this is kind of an intermediate product, or you don't need to think about that anyways, because I said until no further oxidation takes place. So the product that I get finally is going to be this product. Okay, and now I just look at which option matches with it. So this one, it has 3 carbons for some reason, so that is immediately wrong. This one has 2 carbons, this one has 2 carbons as well, this one also has 2 carbons, so that's great. And this one, it still has the aldehyde group for some reason, D, so I'm not considering that. This one again, why does the OH not get oxidized? That's so weird. So again, C is cancelled. As for B, it seems to be the same product that I got, so I'm going to say B is the answer. And then as for A, yeah, again, I already cancelled out A because it has 3 carbons, which is kind of weird because you're not adding cyanide or something, so it can't increase in the number of carbons, right? So that has to be wrong. So B is going to be your answer in this case. Now let's go to the next question. An ester with an odor of banana has the following formula. Which pair of reactants, under suitable conditions, will produce this ester? Okay. So let us see. So, I mean, if I draw it out, I have CH3COO, CH2, CH2, CH3, CH3. So I mean, either I could have it as CH3, C, O OH plus CH3 CH2 CH CH3 CH2 OH, I guess. Or I could have it as CH3 CH2 OH plus CH3 CH2 CH CH3 C O OH, if I'm not mistaken at least. But yeah, okay, so here I have methanol, which makes absolutely no sense. I mean, you can see I have either ethanoic acid or ethanol. So, A, B, C, or D, they should include either ethanoic acid or ethanol. First one includes methanol, so I can cancel that out immediately. I don't see any ethanoic acid or ethanol. Here I see ethanol, so I'm not canceling out this option currently. Here I also see ethanol, so actually that's ethanoic acid, sorry. So I'm not canceling out C either. As for D, I see ethanoic acid as well, so I'm not canceling that out either. But I don't know, am I doing something wrong? I'll check. So I have 1, 2, 3, 4, 5 carbons in my other part. 1, 2, 3, 4, 5. So I should have 5 carbons. So 1, 2, 3, 4, 5, which I do have here. And 1, 2, 3, 4, 5 carbons here as well. 1, 2, 3, 4, 5 carbons here as well. So now let's see where the group is attached. I mean, if I have ethanol, okay, so firstly, also yeah, oic acid and alcohol, oic acid and alcohol, oic acid and alcohol, that's all right. And I do feel like I am making one small mistake. Am I not? Wait, let me just draw out this molecule. CH3, CO, O, CHH. Oh, yeah. I am making a mistake. Okay. CH, CH3, CH2, CH3. Yeah. Sorry about that, guys. If you divide it like this, then you see clearly that you have to have H3 since it's very. You should actually always draw out the molecules carefully. I mean, it cannot have an ethanol, then it has to be ethanoic acid that's present, basically, because you have CH2O, and that means this part has to be the alcohol part, and then you have COO, so that has to be the carboxylic acid part. So I'm sorry for making that mistake, but then that means that you have to cancel out option B as well. And so we only have the ethanoic acid options left, right? And yeah, I'm sorry about that mistake, but yeah, just draw out the molecules carefully. Now let's see a 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, I can see that the CH3 group is connected differently, so we should just see carefully where the CH3 group should be. So I mean it should be CH3, CH2, CH, CH3, CH2OH. So CH3, CH2, CH, CH3, CH2OH, that seems right. CH3, CH, CH3, that's wrong. So in the structure that I've got, it corresponds to C. So yeah, just be careful, and I mean don't do things in a hurry. I mean, obviously from this one you're not going to get either ethanoic acid or ethanol. No, you have to consider that you have to get one of them because the molecule divides like this, right? Like this, CH3, and you have CH2O, and obviously that side has to be the alcohol side, whereas the other side has to be the carboxylic side. So be careful, guys. Okay. Anyways, the answer is going to be C. So the next question now: the hydrolysis of one chloropropane to produce propanol is much slower than the corresponding hydrolysis of one iodopropane propane. Which statement explains this observation? So let's see. Chlorine is more electronegative than iodine. Chlorine, chlorine, bromine, iodine, acetane. Well, I mean, from what I remember, like the trend that you have across the period is that electronegativity increases with down a group. Your electronegativity actually decreases. So chlorine, yeah, it is more electronegative than iodine, definitely. But does that really explain the observation? Is the question. Um, hmm. Bond strength of the Ci bond is less than that of the CCl bond. Well, think about this: if you have carbon and you have carbon and then you have iodine versus you have chlorine, so you can see that iodine is much bigger atom as compared to chlorine, right? So iodine If it's a bigger atom, that means the CI bond, because the internuclear distance is greater, so the bond length is greater, which means the bond strength is less. So bond strength of the CI bond is indeed less than that of the CCl bond. And I do believe that makes more sense than the first option, because you have to see which statement explains this observation, not necessarily which statement is correct. Because yeah, I feel like the first statement, it is also true, but does it explain anything? So it doesn't really explain the observation, the observation that they've made in the stem of the question, right? Doesn't explain, right? Whereas this one, it does. The bond strength of the CI bond is less than that of the CCl bond, which means that the CI bond breaks more readily, and because it breaks more readily, then the hydrolysis of one iodopropane be faster as compared to the hydrolysis of one chloropropane, right? And relatively, and yeah. And as for C, the carbon atom in the CCl bond is more partially positive than that in the CI bond. Yeah, again, that is true, because um your CCl bond is more polar than your CI bond, but because again, yeah, polarity also decreases from the group, as I remember. But then the thing is, again, it doesn't really explain the statement, does it? Because the only one of these that really explains the observation properly is option B, in my opinion. But there's also like a D. The hydrolysis involves a nucleophilic addition reaction. That definitely has to be wrong. I mean, the hydrolysis of one, like if I have one iodo propane or something, and then that's being hydrolyzed, right? So, oh wait, I don't know if I drew the right product or not, but then the big point is that because hydrolysis, right? Is hydrolysis is breaking down using water. I mean, should be fission. Asha. Anyways, the thing. What was I going to say? Yeah, I was going to say that it's not a nucleophilic addition reaction in either case. I think it should be like a substitution, maybe something, right? Because that one is bringing in stuff. So it is substitution, and I drew this wrong as well, because it should have propane. So there should be one more carbon. But anyways, nucleophilic addition usually just occurs for aldehydes, no matter what the reaction mechanism is. Because I don't know why my brain is not working right now, but the nucleophilic addition will only be for aldehydes and ketones, right? Nucleophilic addition is for aldehydes and ketones, as you know, and therefore D is definitely the wrong statement. A and C, I still feel that they're the right statements. They just don't really explain the observation very well. So therefore B is going to be the answer, because that makes the most, well, sense in terms of it explains the statement best. Okay, and let's go to question number 24. There are three structural isomers in the formula C5H12. Which formulae correctly represent these three structural isomers? Okay, so let me draw them out. Firstly, they're all alkanes, right? Because it's CnH2n plus 2. So they're all alkanes. So firstly, I can have this M, right? So that's one isomer that I can have. Then I can have something like a butane with a branch. So that's another isomer. And then I can have propane with two branches. Okay, so that is three isomers that I can see. And then let's see which of these matches. Well, I can definitely have CH3, CH2, 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 CH3. So all of them have this. So currently I can eliminate no option, because all of them have this. As for the second isomer, it should be a butane thing. So CH3, CH2, CH3, that's wrong. CH3, CH2, because there should be in brackets, right? The branch should be in brackets. CH3, CH2, CH, CH3, CH3 doesn't make any sense, because the branch I can see here is CH3, right? So yeah, CH3, CH, CH3, CH2, CH3, there's a CH3, CH, CH3, CH2, CH3, both of those are the same, isn't it? So yeah, again, I cannot eliminate an option currently. I mean, now I've eliminated A and B at least, but now I'm looking at C. So then that should be a propane isomer which has two branches. So CH3C, CH3 twice. CH3, whereas this one is CH3, CH2, CH3. CH3, is it the same as the second one? I don't know, but that's kind of weird. Why would they write the same one twice? Never mind, but D is also wrong, therefore. And so your answer is going to be C, because that's the only one that has 3 correct isomers. Okay, now let's go to the next question. CH3, CH2, CO, CH2, CH3. Let me just draw that out because I've learned from question, I don't even remember which question it was. Yeah, 22. That it's really important to draw things out, okay, and not do things in your mind and then mess them up later. Yeah. Okay. So I've drawn this molecule out and it reacts with hydrogen cyanide. And now this is nucleophilic addition, a classic case of nucleophilic addition. You have a ketone and you have hydrogen cyanide to form an ionic product or organic product, sorry, called a cyanohydrin. Which feature applies to the cyanohydrin product? Now this nucleophilic addition gives you the product CH3, CH2, COH, CN, CH2. If I remember correctly, this is a product that you get. CH3, and yeah, I do realize that I accidentally wrote CH2 there. It should be CH3. Okay. Which feature applies to the cyanohydrin product? It has one chiral center. Well, this cannot be a chiral center, this cannot be a chiral center, this cannot be a chiral center, because chiral center has to have 4 different groups attached to it, right? The carbon. This cannot be a chiral center. This carbon, on the other hand, it has one OH group attached, one CN group attached, but on this side it has CH2, CH2 attached, and on this side it also has CH2, CH3 attached. That means it has 2 identical groups attached to it. Like, yes, okay, OH and CN are different, but then CH2, CH3, it has 2 of those groups, to CH2, CH3 groups attached to it, 2 ethyl groups attached to it. It means it cannot be a chiral center, right? As for the second thing, it is formed by electrophilic addition. No, I already mentioned it's nucleophilic addition, right? It's not electrophilic addition. Because HCN generates the cyanide nucleophile. Nucleophile, it's kind of obvious. It has a lone pair, it has a charge, and it's a nucleophile. So yeah, it's nucleophilic addition, not electrophilic addition. And it is formed via an intermediate which contains the COH group. Its formation requires the use of cyanide ions as a catalyst. But I mean, it is formed via an intermediate which contains the COH group. I should probably draw out the mechanism in that case. Make some space somewhere. So, I have, well, firstly, I mean, if it's reacting with hydrogen cyanide, I would get hydrogen cyanide kind of in, having an equilibrium, because this is partially positive, this is partially negative. So you can have like electron transfer from the hydrogen to the cyanide, like, what I would get basically is H plus and Cn minus. Yeah. Other than that, if I look at the mechanism, then I have CH2, CH3, CO, CH2, CH3, right? And I have 2 lone pairs on my oxygen, of course. So what I do is that, okay, so now I have cyanide, right, from this equilibrium. I'll use a different color maybe. And what this cyanide does is it attacks this partially positive carbon. We should write partially positive here and partially negative on the oxygen, but then it attacks this partially positive carbon because obviously cyanide is a nucleophile, it is nucleophilic addition after all. And then what happens is that this bond breaks, right? This double bond breaks from a single bond. And so the intermediate that you get from this is CH2, CH3, CO, 1, 2, 3 lone pairs with a minus sign. Of course, charge is preserved in your mechanism, remember that. And you have Cn attached here, and then you have CH2, CH3. Right. So you get this oxyanion, and it's very horrible writing, but this says oxyanion intermediate. right? And obviously I yeah, then I mean, if you want to further continue the mechanism, then I have another HCNI, and there that, well, this oxygen lone pair, I mean, okay, my drawing is not the best, but then oxygen, grabs the hydrogen, and then this bond breaks, so it's kind of like a protonation, right, like acid base reaction. And then you have CH2 CH3 here, C, and you get OH there, and you have CN here, and then you have CH2 CH3, and then you have cyanide again, right? So its charge is preserved, and you can see that HCN is acting as a catalyst, kind of, or actually not HCN specifically, but okay. So I mean, if you look at it's cyanide, because cyanide is being reformed, I guess you could say, but yeah. Anyways, it is formed via an intermediate which contains the COH group. That is wrong. The intermediate is oxyanion, as I mentioned, it has the CO minus group. So C is also wrong. D, on the other hand, its formation requires the use of cyanide ions as a catalyst. As you can see, we used cyanide ions, which we gained from the HCN, equilibrium. We used cyanide ions and we gained back cyanide ions as well. So yes, it's very obvious that yes, cyanide is acting as a catalyst because it's not used up in the reaction. Like at the end of the reaction, you still have cyanide, basically, yes. So D is the correct answer. And let's go to the next question. Question number 26. Just erase some things. How many moles of oxygen molecules are needed for the complete combustion of 1 mole of 3-methyl pent-2-ene? So let me draw the molecule. So I have pent. I'm drawing a skeletal structure because I like skeletal structure, and I have a double bond on the second carbon, so second and third is a double bond, and I have a methyl branch on the third carbon, so something like that. And so if I write down the molecular formula of this compound, so I have 1, 2, 3, 4, 5, 6 carbons, so C6. How many hydrogens do I have? H1, 2, 3, 4. No hydrogens there. 5, 6, 7, 8, 9. So I have 9 hydrogens. Let me just count again. 1, 2, 3, 4, 5, 6, 7, 8. Oh, 9. And then I also have these 3, 10, 11, 12. So it should be H12. That makes a lot more sense considering it is a alkene. It is an alkene. So, it should be CnH2n. So that makes much more sense. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, that makes much more sense. Okay. So don't be like me. Use your chemical intuition. All right. Then let us consider its combustion. So we should add oxygen there. And then we obviously get combustion products, which are CH2 and H2O, right? And so how many carbon molecules have 6 CO2, because I have 6 carbon atoms in C6H12. As for H2O, well, I have 12 hydrogens. So on the right hand side, I should also have 12 hydrogens. There should be 6 H2O because 6 times 2 is 12. And so how many oxygens do I need then? Well, I have 6 over here, and then from the CO2 I have 6 times 2, which is 12. So 12 plus 6, and that is equal to 18. So therefore I should have 18 oxygen atoms on the left hand side as well, and I have O2. So then 2 times 9 is equal to 18, or 18 divided by 2 is 9. So that means that I should have 9 O2 if I am not mistaken. Therefore, how many moles of oxygen molecules are needed for the complete combustion of 1 mole? It's 1 mole of 3-methyl-1-pent-2-ene. That should be 9. If I did not count wrong, which I hopefully did not. But anyways, let's go to the next question. The hydrocarbon C17H36 can be cracked. Which compound is the least likely to be produced in this reaction? Well, least likely to be produced, you have C3H8, C4H8, C8H16, C16H34. You're very much likely to have smaller cracking products, like smaller alkyls. That's kind of the point of cracking as well, right? Like C3, C4, C8. Those are quite small numbers relative to 17. So those are what nonsense? What just happened? Wait, cancel. Okay. So anyways, those are more likely because they're smaller numbers, where 16 is quite close to 17. So it's a less likely cracking product, because you would want a smaller alkene as a result of cracking, right? I'm going to say the answer is D from that logic. Like C16H34 is the less likely product of the cracking. Okay. Anyways, let us go to the next. Obviously, they're all possible products, probable products, but then this is less probable, basically. Anyways, compound X has the molecular formula C4H10O2. X has an unbranched carbon chain and contains two OH groups. On reaction with an excess of hot acidified aqueous manganate 7 ions, X is converted into a compound of molecular formula C4H6O4. So that's, oxidation. So to which carbon atoms in the chain of X are the two groups attached? Okay, so we shall draw this compound. It has an unbranched carbon chain and it has two OH groups. Now, because it is oxidized in such a way that it gets two more carbons added, because for example, if I had oxygens OH on the second and third carbon atoms, then when you oxidize it completely, you would get ketones. So you would have an oxygen there, you would have an oxygen there, double bonds, and that is problematic because the molecular formula here shows you four carbon atoms or oxygen atoms, right? So it cannot have oxygen atoms on the second and third positions because two oxygens from C4H10O2 became four oxygens in C4H6O4. So therefore, option A must be wrong, option B must be wrong, option D must be wrong, so it must be C, basically. But then if you look at that structure that you would have, where you have OH on the first and the fourth carbon atom, then when you oxidize that completely, you get, complete oxidation, so then you get carboxylic acids, right, from primary alcohol, so then that becomes this structure. And as you can see, you have two oxygens added here, right? So you had four oxygens, and if you count everything, 1, 2, 3, 4, so that's C6H, 1, 2, 3, 4, 5, 6, 6, and sorry, why did I write 6? There should be 4, then C4H6, and then O again, 1, 2, 3, 4, so that's 4. So I hope that makes sense, and that is going to be the answer. Okay, let's go to the next question. How many geometrical cis-trans isomers are there of hex 2,4-diene, CH3CH double bond, CH double bond, CH3? So what do you do? What is a good strategy to do is just draw everything out, because honestly, drawing things out really helps. Okay, I would always advise to draw things. Anyways, so you have 1, 2, 3, 4, 5, 6, right? And you have double bond at the 2 position, at the 4 position. So let me just make double bonds second position and also at the 4th position, right? And then once it's trans isomer, so firstly this one is the trans isomer, right? Because you can see the two groups are opposite to each other. So yeah, and the two, CH3 CH3 and like the higher molar mass groups are opposite to each other. The trans to each other is the proper term, I suppose. I don't know why I'm trying to find new terminologies, but anyways, that's that. And then 1, 2, 3, 4, 5, 6, yeah. So this would be your cis isomer, because as you can see, these two groups are cis to each other and these two groups are cis to each other as well, right? So that's 2 already. And then I can have another one, which is if firstly this first group is cis and the second group is trans. So 1, 2, 3, 4, 5, 6 carbon atoms, and then this part is trans, so we have T, and then this part is cis, right? So we have trans, cis, and then on the other hand, I could have the first group as cis, so like this, and the second group as trans, like that. However, you have to realize that hex 4-diene is a symmetrical molecule, right? On the left side, it's the same as the right side. I mean, yeah. So therefore, actually, your trans cis and your cis trans, both of these isomers are actually the same, right? Um, I hope you understand that point. It's quite a subtle point, but it's true. So therefore, I have one isomer, I have second isomer, and these two are equivalent. So I have in total 1, 2, 3, 3 isomers by tallying. So my answer is going to be C then. Okay. Next question. Butanoic acid can be produced from 1 bromopropane using reagents X and Y as shown below. So what could be reagents X and Y? So let me just draw out one bromopropane, which is this is the skeletal structure. And then as for butanoic acid, this is the skeletal structure. As you can see, carbon has been added, right? Like propane has 3 carbons, whereas butanoic acid has 4 carbons, right? So if I'm adding a carbon, what reagent do I use? Well, obviously, I need cyanide, right? So definitely I should choose an option which has cyanide there, and I can only see A and B having KCN and ethanol, which is the reagent to add a cyanide, like, right, by nucleophilic substitution. And therefore, that means that firstly, I should cancel out C and D because those are definitely wrong because I need a cyanide to be added, okay? So either going to be A or it's going to be B. The second thing is that, okay, so after reagent X being KCN and ethanol, that means I get CN as, I get this compound as my compound Q, right? But then I need butanoic acid from that. So how do I get butanoic acid? Well, obviously I need to do hydrolysis, but do I do acid hydrolysis or base hydrolysis? Basically, is the thing, right? I hope I'm using the right terminology. I don't know why I'm so confused about hydrolysis now in this whole paper, but anyways, the thing is that if you think about it, if I do base hydrolysis, that means that I would get O minus Na plus as my product because the OH, right? So the H should be taken by the OH minus that's present in the solution so that you form water basically. And so your product would actually be a um carbo, why am I forgetting the terminologies? Carboxylate ion, right? A carboxylate anion rather than a carboxylic acid. That's the problem with base hydrolysis. Whereas in acid hydrolysis, well, I have the product as OH, and obviously, like if I have H plus present in the solution because I have H plus Cl minus, then H plus is not going to take an H plus, right? Like why would it do that? It's already H plus. Whereas in base hydrolysis, you have Na plus OH minus, and this OH minus is quite willing to take the H from your carboxylic acid to give you the carboxylate anion, right? So if I want butanoic acid and don't want butanoate anion, then I must use acid hydrolysis, if you get my point. So therefore, the answer is going to be A. Okay? Okay. Now let's go to the next question. Part B. So, user data booklet is relevant to this question. When the liquid N2F4 is heated, it decomposes into a single product X. Which statements are correct? So N2F4 would be something like this, I presume. Because fluorine, like halogens in general, like to form single bonds in general, and we want nitrogen to have 3 bonds ideally. So I would predict this to be the structure. And you wanted to decompose into a single product. What could the product be? I guess it could be something like, I don't know, NF2 maybe, I think. 2 NF2. Does that make sense? Maybe, I don't know, 2 NF. I don't know if that's a very likely product. I mean, because nitrogen is forming 2 bonds, but then you would have like a lone pair or something, right? So maybe it is a likely product. I don't know honestly. But anyways, NF bonds are broken during this decomposition. Well, according to me, it seems like the NN bond is definitely breaking, but not really the NF bonds. I'm going to say one is wrong. The enthalpy change when N2F4 decomposes into X is approximately plus 160 kilojoules per mole. Well, the change that is happening is NN bond breaking. So let me see what is the bond energy of the NN bond. You can find it in the data booklet probably. This is the note papers I'm allowed to use, the data booklet. NN, single bond energy, right? Single bond NN. Oh, that is 160. So I guess you were right about the structure anyways. So then, yeah, I mean, if the NN bond is breaking, well, bond breaking, um, what's it called? Bond breaking is endothermic. It requires energy, whereas bond formation is exothermic. It releases energy, right? So obviously, if this is bond breaking, that implies that you will have positive. So positive, and then 160 is the bond energy. So positive 160 kilojoules per mole to break the NN bond, right? So B seems to be right. As for C, molecules of X are non-linear. Well, I got X as NF2. If I do the hybridization and like steric number check on it, the steric number is okay. So I have one sigma bond, two sigma bond on bonding to nitrogen, like one sigma bond, two sigma bond, and then have a one lone pair. So the steric number is 2 plus 1, which equals to 3. If it has a steric number of 3, that means it has a hybridization of sp2, and so it likely has a trigonal pyramidal, trigonal planar configuration, but because of the lone pair, it's not trigonal planar, it's going to be a bent molecule, right? So to say that molecules of X are non-linear, that is definitely true because it is bent. I mean, well, honestly, trigonal planar also means non-linear, but you know what? 3 is right, is the point. So 2 and 3 are right, therefore my answer is going to be C. Okay? Now let's go to the next question. P and Q are two liquid compounds with similar MR values. Molecules of P attract each other by hydrogen bonds. Molecules of Q attract each other by van der Waals forces only. How do the properties of P and Q differ? So they are liquids with similar MR values, and P has hydrogen bonds, right? Because of that, can I say that P has a higher surface tension than Q? Definitely, because of the hydrogen bonding. It is going to have a higher surface tension because that's kind of similar to how water is, and water also has a high surface tension compared to something that does not have hydrogen bonding, like I don't know, hexane or something. P is less soluble in water than Q. That is wrong because again, P has hydrogen bonds, water H2O, HOH, because hydrogen bonding is bonds like in compounds which have hydrogen and also one of the three most electronegative elements, that's either fluorine or oxygen or nitrogen, right? So if you have this, then you have hydrogen bonding. I mean, in water, you obviously have that because you have the OH bond, which has oxygen and hydrogen, right? So to say that P is less soluble in water than Q, that's wrong because P has hydrogen bonding and water also has hydrogen bonding. So if they both have hydrogen bonding, that means that P is soluble in water that has hydrogen bonding, whereas Q, it does not have hydrogen bonding, it only has van der Waals forces, so therefore Q is the one that's not that soluble in water, right? P has a lower melting point than Q. That is also wrong because again, P has hydrogen bonding. Hydrogen bonding is a stronger uh, intermolecular force of attraction, and because it's a stronger intermolecular force of attraction, that means that it will take more heat, more thermal energy to melt P than it will to melt Q. Therefore, P has a higher melting point than Q. So therefore, 2 and 3 are wrong. Since only A is right, that means I think D will be the answer, right? If I'm not mistaken. Yeah, 1 is only correct. So D is the answer. 1 only is correct. 1 is only correct. How did you state it? 1 only is correct. That sounds like a check in bags. Actually, R and S, they always write, this amount only and stuff. But anyways, R and S react together. R plus S gives you T. So which factors affect the rate of the forward reaction? The activation energy of the reaction? Uh, Definitely, I would say that does affect the rate. If you have a lower activation energy, then your rate is faster, and that's the purpose of a catalyst, to increase the rate by lowering the activation energy and stuff, right? The Boltzmann distribution, so cool. just lower the activation energy. That's not a very accurate diagram, but if you look at one of the very first questions in this paper, I think we get an explanation of that. The enthalpy change of the reaction. The enthalpy change of the reaction is concerned with the thermodynamics of the reaction, not the kinetics, but the rate. Rate talks about the kinetics, right? So enthalpy change should not really affect the rate of the reaction, nor can it really be changed by something like temperature or surface area. Enthalpy change is quite a fixed value in a way, I guess, but it's not that flexible as a kinetic property would be. Anyways, that's wrong, basically. The equilibrium constant of the reaction, again, yeah, it depends more on the thermodynamics of the reaction, not the kinetics. Equilibrium constant, again, it's the ratio of the concentration of the products over the concentration of the reactants, right? So, I mean, you can't really, it does not really affect the rate of the forward reaction. We're talking about the rate. It's very important. Rate depends on things like temperature, catalyst usage, surface area of the reactant molecules, like if there's small powder particles or if they're larger particles and stuff like that. So that's why 2 and 3 have to be wrong. And therefore, since only 1 is correct again, our answer is going to be D. Here's the next question. The Bronsted-Lowry. Oh, what happened? Why is my screen black all of a sudden? Okay, it's black. The Bronsted-Lowry theory describes acid and base character. When concentrated sulfuric acid and concentrated nitric acid are mixed, the following reactions occur. Which species are bases in these reactions? So bases, we know according to the Bronsted-Lowry theory at least, that bases are proton acceptors, right? So I have to find species that are accepting H plus. Okay, so if H2SO4, that is obviously an acid, and therefore the other compound must be the base. And then you have the conjugate base of H2SO4 is being HSO4 minus, which has one less hydrogen, of course. And as for H2NO3 plus, you can see it has one more proton than HNO3, so therefore this has to be the conjugate acid of HNO3. So what can I say? Which species are bases? Well, do I have HSO4 minus as a base? It is a base. It's the conjugate base of H2SO4. So 1 is right. As for HNO3, yeah, it is a base because I can see in the HNO3 is acting as a base in the left-hand side of the first equation, right? HNO3 is definitely also acting as a base. And as for NO2 plus, well, NO2 plus is not in the first reaction, but let's look at the second reaction maybe. H2NO3 plus is becoming H2O and NO2 plus. So, well, I mean, if I look at it like this, like NO2 plus H2O, like in the backward reaction basically, gives you H2NO3 plus. Technically, NO2 plus is gaining a water molecule, right? Gaining water. And water is a it's a neutral molecule, right? So it has H plus as well as OH minus. It's neutral. Therefore, if NO2 plus is reacting with water, which has H plus and OH minus, that means that basically this is not an acid-base reaction, I would say. It seems to me that it's not an acid-base reaction. Because it's NO2 plus is not acting as an acid or as a base. H2NO3 plus also is not acting as an acid or a base. So this is kind of an indecisive reaction, or unhelpful in a way here. Anyways, if you look at the third reaction, well, here I have H2SO4 plus H2O giving you H2SO4 plus and minus an H3O plus. H3O plus is again, yeah, just another, it's hydronium ion, and that is obviously an acid, so this is acid. And then the conjugate base of that is water. As for H2SO4 minus, that's a base, obviously, if it's reacting with the acid, and this is going to be its conjugate acid, H2SO4. So, I mean, yeah, here you have water acting as a base, and you have H2SO4 minus acting as a base, and I've already selected 1 to be right. So 1 and 2 are definitely right, but then NO2 plus on the other hand, NO2 plus it seems is acting as a neutral molecule because in the second reaction, you don't have an acid-base reaction. Therefore, which species are bases in these reactions? It's only HSO4 minus and HNO3. Therefore, I'm going to say the answer is, well, 1 and 2 are right, so that means my answer should be B. All right. B is going to be my answer. Okay, let's go to the next question. Question 35 now. Pollutant oxide Y, which contains non-metallic element X, is formed in a car engine. Further oxidation of Y to Z occurs in the atmosphere. In this further oxidation, 1 mole of Y reacts with 0.5 moles of gaseous oxygen molecules. X could be either nitrogen or sulfur. So which statements about X, Y, and Z can be correct? Well, it can be either nitrogen or sulfur, right? So let me just try with sulfur first. So S plus oxygen, okay, gives you the pollutant oxide Y, which is SO2 in the first case, and then the second equation you get is going to be SO2 because you have further oxidation, right? So SO2 plus O2 giving you SO3, and this is actually, we know from the contact process this is a equilibrium reaction. And now if I balance the number of moles and stuff, so I have 3 oxygen atoms on the right hand side, so therefore I should have 3 on the left hand side as well. So first I make this 1 by 2 O2, right? And as for the case of nitrogen, I could have N plus O2 giving me again, well actually not again, but actually giving me NO, no, right? So yeah, and then in the case of further oxidation, I get NO plus again 1 by 2 O2 giving me NO2, right? So those are equations that I hope you've seen before. Ideally, so this is going to be X, this is going to be Y, this is going to be Y again, and this is going to be Z. This is going to be X, this is going to be Y, it's going to be Y again, and this is going to be Z, right? So now let's read the statements. The oxidation number of X increases by 2 from Y to Z. Let me see. So over here, because oxygen, we know I'm going to use a different color, maybe. So we know that oxygen has a fixed oxidation state usually of -2. So -2, and then you have 2 oxygen atoms. So I'm going to multiply this by 2 plus, and I'm going to take sulfur as having oxidation state of X equals to 0. So then from this you get X equals to +4, right? So over here, sulfur has an oxidation state of +4. Similarly, for the case of SO3, we again know that oxygen has a fixed oxidation state of -2 usually, and then because there are 3 oxygen atoms, so I'll multiply this by 3, then I'm going to make the oxidation state of sulfur as plus X, and then equals to 0, or just X, I mean to say. And so then, because overall oxidation state is going to be 0, right, of the SO3, because it's a neutral molecule. So then you're going to get X here as +6. So we can see that sulfur here has an oxidation state of +6. So you're going from +4 to +6. So the oxidation state of X increases by 2 from Y to Z. That is true in the case of sulfur. Now let's check the nitrogen case. So Y over here is going to be N, and oxygen again has a fixed oxidation state of -2. So then nitrogen is going to have +2, so as to maintain the overall molecule as having 0 oxidation state because it is a neutral molecule, right? And in the case of NO2, the case of NO2 is quite analogous to the case of SO2. So then you're going to have again the oxidation state over here as +4 as we had for SO2. And so we're going from +2 to +4. That is again an increase of 2. So by increase by 2 from Y to Z is true in the case of both both sulfur and nitrogen, right? So statement 1 is right. As for statement 2, Y has an unpaired electron in its molecule. Y is SO2 firstly, and also NO2, right? So if I draw out SO2, so I mean you have oxygen and then you have another oxygen, right? And I would assume that there are double bonds here, but that would be the most probable structure in my opinion. And then you have 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's too many electrons. Let me say it's 1, because sulfur it's in group 6, right? So it has 6 electrons in its valence shell. So 1, 2, 3, 4, 5, 6 are the octets complete? Let me just, this is a Lewis structure I predict. So then 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons around oxygen. As for this one, again, you have 8 electrons around this oxygen as well, and sulfur you also have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But sulfur can have an expanded octet. You can read about this topic if you want. Expanded octet, I think it's a topic that you get introduced to in the beginning of AS maybe. But yeah, sulfur is allowed to have an expanded octet because it is in group, I think 3 or so. I don't know. Magnesium, aluminum, sulfur, silicon. Yeah, it is in group period 3, sorry, period 3. So therefore it is allowed to have an expanded octet, right? And yeah, so that is true in the case of sulfur. As for the case of nitrogen, in nitrogen's case, the compound Y is nitrogen monoxide, so NO. Now what is the Lewis structure for nitrogen monoxide? Well, I mean, you could have oxygen having a lone pair maybe, and then you can have a double bond. Double bond, would that be a completed, maybe we should make a triple bond. I'm not drawing data of covalent if not needed, but let me see if this is a complete octet. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons around nitrogen, and then you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons around oxygen, so that's too many. So let me kind of make it as maybe we could kind of. But the problem is that nitrogen has 5 electrons in its valence shell, and oxygen has 6 electrons in its valence shell, and that makes it 11 electrons in total. So it's going to be, you're going to have a radical somewhere. Like there will be an electron that is not a lone pair, kind of, is my point. There's an electron that's not in a pair. So maybe you can just draw it as something like this, and then you have still the oxygen and this lone pair, and then you have a double bond, because then you would have 1, 2, 3, 4, 5, 6, 7, 8 electrons around oxygen, which is great. As for nitrogen, you have 1, 2, 3, 4, 5, 6, and then you would have 7, which is kind of fine, right? Or the other structure that you could possibly have maybe is NO double bond, because triple bond is not possible because again oxygen is in pair 2, so it cannot have an expanded octet. So therefore you cannot have 10 electrons in the valence shell of oxygen. Like it cannot have that expanded octet because 2 cubed equals to 8. Like it just cannot have an expanded shell. Like the number of electrons that an atom can have in its shell is basically 2n squared in its shell. And so for oxygen, since it's in period 2, where n is your period number, like principal quantum number or shell number, basically, you get the point. So then for oxygen, it's in period 2, right? So it's going to be 2 into 2 squared. So that makes it 2 cubed, that's 8. So that's why I said that it can only have a maximum of 8 electrons in its valence shell. As for nitrogen, it's the same case because nitrogen is also in period 2. Whereas sulfur is in period 3, right? So it can have 2 into 3 squared, which equals to 2 into 9, which equals to 18 electrons maximum in its valence shell. So that is the logic that I was talking about. So that's why I'm saying that oxygen and nitrogen cannot have expanded octets, okay? Anyways, NO, and then so I'm just drawing another possible structure for nitrogen monoxide, because I could either have this random, not random, but this unpaired electron on nitrogen, or I could have it on oxygen as well. So in that case, I would have it something like this, and then nitrogen would have 2 lone pairs, right? 1, 2, 3, 4, 5, 6, 7, 8. Now in this case, nitrogen has 8 electrons, whereas oxygen has 1, 2, 3, 4, 5, 6, 7, so 7 electrons around it. And I suppose these two would be in, I guess resonance is not a big thing of AS or A level chemistry, I think, right? But anyways, these are kind of in resonating structures, resonance structures, basically resonance structures. You could research about that as well. Research resonance is really cool. Resonance is really, really cool. So what was I talking about? Yeah. So the statement says that Y has an unpaired electron in its molecule. Well, is that true in the case of sulfur? An unpaired electron. I mean, don't really see an unpaired electron as such, but they did say, but there's an unpaired electron for oxygen. I mean, they did say X can be either nitrogen or sulfur. I mean, does that basically mean that you have to consider each case separately, and if it is satisfied for either nitrogen or sulfur, then you say that the statement is true. Because if you look at the, I feel like this is a very tricky question in the sense of the wording, not the concept. But you know, this just say which statements about X, Y, and Z can be correct. So it's possible to be correct. So I mean, for sulfur, I don't really see an unpaired electron as such. Maybe if you check the electronic configuration, but then again, you see this electron pair, right? So I can't really say that it's a true statement in the case of sulfur. So in the case of sulfur, it's not true. But in the case of nitrogen, you can clearly see this one that I've highlighted in pink. This, you have an unpaired electron. So I can say that this statement can be correct because it's true in the case of nitrogen, right? So this statement definitely can be correct if you look at the terminology of the question very carefully. But really, it's quite a weird question. But anyways, 1 and 2 are right till now. And why? Third statement is Y is a polar molecule, right? So if I look at sulfur, oxygen, and versus nitrogen, oxygen, I mean, yeah, the five most electronegative atoms are fluorine, oxygen, nitrogen, chlorine, bromine. I mean, the only thing is, I don't think that the data booklet, this one that I have, it gave you Pauling electronegativity values, right? Why is it upside down? Okay. So I don't think this one gives you Pauling's electronegativity values, but I can. Oh, what happened? Just a second. There are technical difficulties apparently. Okay, sorry about this. But definitely, what I can say is that there is an electronegativity difference. So they are kind of, you can consider them polar in that way. As for sulfur dioxide, if you consider the electronic sorry, the hybridization around it, this is one sigma bond, two sigma bond, and you have a lone pair. So your steric number, which is the number of lone pairs plus the number of sigma bonds, is 2 plus 1, which equals to 3. So that implies an sp2 configuration. So it would be predicted to be a trigonal planar structure. However, because of the lone pair, it is bent, not trigonal planar. So that's one thing. And why am I doing that? I'm just kind of to show that it's not really a, I don't know. I mean, it seems like a symmetrical molecule to me, right? Because even if it bent, it would be bent in the same way, like 120 degrees minus 2.5 degrees approximately is going to be about 117.5 degrees, maybe. I don't know if my mental math is that bad, but yeah. And in the case of nitrogen, I mean, you don't really have an angle, do you? It is definitely a polar molecule, however, because oxygen is more electronegative than nitrogen, and I can say that this is partially negative. Nitrogen is partially positive then, and so you have a dipole going kind of there, maybe. I mean, that's the way organic chemists draw it. I mean, I guess the quantum physicists and stuff would draw it in the opposite direction. But anyways, it's plus symbol is how the organic chemists define it. But anyways, uh, NO is quite obviously a polar molecule because it just has a one single bond. I mean, if it has a polar bond, then it's a polar molecule. And if you get my point, so it's you know, because if it's just two atom molecule, so it doesn't have an angle, and so you don't need to worry about polar, you know, dipole moments canceling out. If there's a dipole moment, then you just consider it as a polar molecule. So therefore, I can say that in the case of nitrogen, it is definitely a polar molecule. In the case of sulfur dioxide, I am quite kind of unsure because it might be that the dipole moments cancel out because, you know, I mean, oxygen is definitely more electronegative than sulfur. So you have two dipole moments, however. So one going, you know, from, because oxygen is more electronegative, so oxygen and sulfur, so oxygen to sulfur, you would have one dipole moment. And this oxygen to sulfur, you would have another dipole moment, right? However, the only thing I'm confused about is, would this be considered a symmetrical molecule? I feel like because of the lone pair, it's not going to be a symmetrical molecule, maybe. And because it's not a symmetrical molecule, so your dipole moments would not cancel out perfectly. And so this could still be considered polar, I suppose. So then you can say that even in the case of sulfur, it is polar. That's what I think. But even if that is true or whether it's not true, the nitrogen monoxide, I think that might be polar as well, but I don't know how much is the electronegativity difference between nitrogen and oxygen, because the next most electronegative element after oxygen is nitrogen, so maybe there's not a very big polarity difference. So could I consider it polar? I don't know, but then again, the electronegativity difference between sulfur and oxygen is much more. So then that bond is definitely polar as compared to nitrogen monoxide. But the nitrogen monoxide is also more probable to be polar because it is, just a bond, and there are no dipole moments. You don't have to worry about dipole moments canceling out, I guess. I don't know if I'm just saying random stuff right now, but the point being that I can say that Y is a polar molecule. I do definitely think that it's likely to be a polar molecule, so I don't know, that's my logic. If I'm saying anything wrong, you guys can write it in the comments, but that's what I feel is the answer. And so I'm going to say 1, 2, and 3 are all right. And therefore my answer is going to be A. Okay? Now let's go to the next question. A test tube of HI gas and a test tube of H2 gas are placed together in an environment at temperature T. Which combinations of observations are possible depending on the temperature T? A brown vapor appears in one of the test tubes. No change is apparent in the other test tube. A brown vapor appears in one of the test tubes. A purple vapor appears in the other test tube. No change is apparent in either test tube. If I consider HI versus HBr, right? So the thing is that if you consider down the group 7, so fluorine, chlorine, bromine, iodine, acetylene. So iodine obviously has a much larger molar mass as compared to bromine. So I mean, iodine is a bigger atom than bromine. So I mean, for example, iodine would look something like this, and then bromine looks like something like, sorry, am I doing it the opposite way around? Yes, I am. So iodine looks something like that, and then bromine, however, looks something smaller. And hydrogen, I'll try to make kind of similar size in both cases, maybe. Okay, this is not the best drawing because there should be some overlap kind of shown. So we'll draw that again a bit. Okay, so that's kind of my inaccurate drawing, but yes. So bromine is a smaller atom than iodine, and therefore, if you place a test tube of hydrogen iodide gas and a test tube of hydrogen bromide gas, which is more likely to decompose, depending on the temperature. So I mean, since HI is having a longer bond length, right? So this bond length is longer for hydrogen iodide as compared to hydrogen bromide, just because the iodine atom is bigger. So because of that, longer bonds are actually also weaker bonds. So then HI bond is weaker than the HBr bond, right? So if it's weaker, then it's more likely to break. So if your for a given temperature, your hydrogen iodide is more likely to decompose as compared to hydrogen bromide. And so what will it decompose to? Well, I mean, a brown vapor, that could be something like bromine gas, I guess. And on the other hand, if you're talking about purple vapor, I would assume that's something like iodine gas, maybe. I don't know, I'm just assuming both and trying to compare. So to say that, depending on the temperature tree, if I keep saying tree, is it possible that a brown vapor appears in one of the test tubes and no changes appear in the other test tube? No, that is not possible. Why is it not possible? Because for a given temperature, you have either no change occurring in both of them, so hydrogen iodide does not decompose and hydrogen bromide does not decompose, or hydrogen iodide decomposes but hydrogen bromide does not decompose, because we know that hydrogen iodide bond is weaker than the hydrogen bromide bond. So it's possible that hydrogen iodide decomposes at a higher temperature, but hydrogen bromide still doesn't. Or if the temperature is very high, then it's likely that both of them decompose. So you see the brown vapor and you see the purple vapor. Sorry, so you see the purple vapor and you see the brown vapor. That's what I mean, because purple vapor you will see at a certain temperature if one of them is decomposing, right? Which is hydrogen iodide. If you get my point. So it's not possible that only a brown vapor appears in one of the test tubes and you don't see any change in the other test tube, because brown vapor means that hydrogen bromide has decomposed. But that is not possible that hydrogen bromide decomposes while hydrogen iodide has not decomposed, because hydrogen iodide bond is weaker. So it should be the first one to decompose, or should be the one that is more likely to decompose. I mean, it's kind of also a statistics, I guess you could technically say that this is possible. That's a very, very low statistical chance, like 0.0000 something, something, something. Okay. Anyways, a brown vapor appears in one of the test tubes and a purple vapor appears in the other test tube. That is possible. That means that hydrogen iodide decomposed as well as hydrogen bromide decomposing. Okay. And no change is apparent in either test tube. If the temperature is very low, then yeah, it's likely that both of them don't decompose. So only 2 and 3 are possible. And since only 2 and 3 are possible, your answer is going to be, I think, C, right? Yeah, so 2 and 3 only are correct. So therefore, C is going to be the answer, okay? Now let's go to the next question. Which pairs of reagents will take part in a redox reaction? CH3CO, CH3 plus Tollens reagent, CH3, CH2, CHO plus Fillings reagent, or CH3, CH double bond, CH2 plus bromine. What I can see is that CH3CO, CH3, that is a ketone, and you're reacting it with Tollens reagent, and so this will not even, there will be no reaction. So again, yeah, I mean, otherwise, because Tollens reagent, reagent is basically AgNO3 that is in ammonia, right? So ammonical AgNO3, and so therefore, when you do the reaction, if you have an aldehyde, that is, then you get RCHO, which is the aldehyde, the arbitrary aldehyde plus AgNO3 in ammonia, and then the product that you get is basically RCOOH, which is your carboxylic acid, so it's being oxidized, plus your 2Ag solid, right? So this is going from, because NO3 is NO3 minus, right? And so this is Ag plus. So Ag plus means it's plus 1, and then Ag here is going to be 0. So this is being reduced, right? So this is reduction. And then RCHO to RCOH, so aldehyde to carboxylic acid, that is obviously oxidation. So that would be a redox reaction. However, Tollens reagent is a test for aldehydes, and so since this is a ketone, there will be no reaction, right? So I mean, otherwise it would be a redox reaction if it was a if it was a aldehyde, but since it's a ketone, there will be no reaction, so it cannot be a redox reaction either, because no reaction means no reaction, right? So one is wrong basically. Now if I look at 2, Fillings reagent, again, Fillings reagent is also a test for um, aldehydes, and this time you do actually have an aldehyde, so it will give a positive test. So again, Fillings reagent is like CuSO4 aqueous, right? So I have my arbitrary aldehyde, which means random aldehyde. I'm just taking RCHO. You could also write CH4, CH2, CHO, but I'm just going to take a general case. Plus your CuSO4, which is copper sulfate aqueous, which is Fillings reagent, and then you get the aldehyde to be oxidized, so it becomes RCOOH, carboxylic acid, and your CuSO4 becomes Cu2O, right? This is not a balanced equation, but you could make it balanced anyways. I don't want to do that right now, but you also get somewhere SO4. I guess you could get H2SO4. I don't know, man. I don't feel like balancing it right now. But anyways, the point that I'm making right now is that, yeah, okay, so this is obviously oxidation. And over here is Cu2 plus SO4 2 minus. So this is plus 2. Whereas in Cu2O, no, oxygen has a fixed oxidation state of -2. And then so therefore to make Cu2O a neutral compound which has an oxidation state of 0 overall, so then you want the copper to have a +1 oxidation state, because 2 times +1 is going to be +2, so then +2 -2 obviously equals to 0, right? So then your copper has an oxidation state of +1, so from going from +2 to +1, that is reduction. So yes, obviously this is a redox reaction. So this is a true statement that if you have an aldehyde, firstly you give a positive test of Fillings reagent, so this reaction is possible, and secondly you can see clearly that it's a redox reaction. Okay. And then we have CH3, CH2, CH3, CH double bond CH2 plus Br2. That would be an addition reaction, so you get CH3, CH, CH2Br, and obviously over here you can see kind of that you're in Br2 you have 0 oxidation state, whereas in this compound you would get it. I mean, do I really need to check it? Do I really need to check it? Suppose I could check it, but I don't want to. I will say, I will say that the most the thing I usually like, obviously, usually you see that bromine goes from 0 to -1, or from -1 to 0. I mean, bromine goes from 0 to -1 because it goes from Br to Br minus, and then if it's going from Br minus to Br, then it's going from -1 to 0. So we can kind of assume that this is -1. We can assume this is -1, and what we can do then is we can assume hydrogen, because hydrogen usually has a fixed oxidation state of +1, right? So we can say that, okay, bromine is -1, and I have 2 atoms of bromine, so 2 times -1 plus how many atoms of hydrogen do I have? 2 plus 1, so that's 3. 3 plus 3 gives you 6. So 6 atoms of hydrogen, and those are having a fixed oxidation state of +1, let's say. And then carbon, I have 3 atoms of carbon, and let's say that's x equals to 0. So -2 plus 6 plus 3x equals to 0. I don't know why I'm doing this honestly, but 4 plus 3x equals to 0. 3x equals to -4. X equals to -4/3. Is that possible? But I don't see any reason for it not to be possible. So let's say it is -4/3. And then in this compound, on the other hand, you can again take hydrogen to have a fixed oxidation state of +1. So let's say that this is the oxidation state of carbon in CH3CHBr, CH2Br, okay, -4/3. If my math is not wrong, and hopefully it's not wrong, but I don't know. We'll find out. And then for CH3, CH double bond CH2, we can take again hydrogen to have a fixed oxidation state of +1. And how many hydrogen atoms do I have? 3, 4, 5, 6, again 6, and then plus, let's say, x for carbon equals to 0, which implies that your x equals to -6. So you're going from -6 to -4/3. Well, that means that you are obviously going from a lower to a higher oxidation state. So this means that carbon is being oxidized, whereas bromine is going from 0 to -1. That's the assumption we made. So then that is reduction. So again, if this, you can basically say that this addition reaction is also a redox reaction if you go by this logic, and bromine is likely to go from 0 to -1, I would say, from what we know from our chemical intuitions. I would say that this is also a redox reaction. So 2 and 3 are redox reactions, and since both 2 and 3 are correct options, I will say that C is going to be the answer for question number 37. And let's go to the next question. The molecule responsible for the pineapple flavor used in sweets is CH3, CH2, CH2, COOCH2, CH3. So this time I will be careful and actually draw out the molecule, unlike what I'd done in a previous question, because it is good to draw out molecules and not make mistakes about which of the part of the ester is the um, carboxylic acid and which part of the ester is the alcohol. Okay, so this time I will try not to make that mistake, so I'm going to draw it out carefully. Okay, so let's do that. And now, what statements about this molecule are correct? The name of this compound is ethyl butanoate. Well, we know that the ester part comes at the end when you're naming, and the alcohol part comes in the beginning. So let me see. This is obviously the ester part, right? This left part, whereas the right part is going to be the alcohol part. So let me see how it should be named. Well, the alcohol part is 1, 2, so that's 2 carbons, so it makes it ethyl, and the ester part is 1, 2, 3, 4, that makes it 4, so that's butyl. So butanoate, sorry, so it should be ethyl butanoate. That seems right to me. So this part is correct. Now, this compound is a structural isomer of hexanoic acid. Is that true? Well, it should be, because we do know that esters and carboxylic acids are structural isomers of each other. And this is composed of 6 carbons as well, so it should be a structural isomer of hexanoic acid. But again, if you're in doubt about that, you can simply kind of write this in a molecular formula fashion. So let me write it as C6H. How many hydrogens are there? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So H12, and then O 1, 2, 2. So C6H12O2. Okay, that seems fine. And then you can draw out your hexanoic acid as well. So CH3, CH2, 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 COOH, right? And you can kind of write that in as you can see that if you draw it out, you can actually see that, yeah, there are structural isomers, I guess, but you could also kind of confirm that by checking the molecular formula again. So C6H 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, O2. So yeah, it seems that they look structurally quite like isomers, and they also have the same molecular formula, so that means they must be structural isomers. You could kind of know that from your general knowledge, or you could also check it yourself. So that option 2 is right. And if you look at the third option, when this compound is heated with aqueous sodium hydroxide, the products are butane 1-ol and sodium ethanoate. Well, let me kind of just erase some things and try to. So heated with aqueous sodium hydroxide means that you are carrying out a base hydrolysis, right? And if I carry out a base hydrolysis of this compound, well, I will firstly, hydrolysis will probably give me CH3, CH2, CH2, COOH, right? So that's the butanoic acid, and then on the other side you get CH3, CH2, OH, right? And however, because it's base hydrolysis, so I have OH minus present basically. And what does the OH minus do? It will kind of take this hydrogen that you have. Let me just kind of, I don't know if I can draw it in a better way, but that's not a very accurate way to draw the lone pairs, by the way, because it's OH minus, right? So there should be 3 lone pairs on oxygen. What happens is that you have this as COOH, right? So one of the lone pairs can kind of grab the hydrogen, and then this bond breaks. So what I get then is CH3, CH2, CH2, because it's base hydrolysis, so I get COO minus, and let's say plus H2O if you want. And then on the other hand, nothing like that can happen to my alcohol, I think. Hope. So it kind of just remains as it is, right? I think, if I'm not wrong. Maybe, I mean, our alcohol is acidic. I don't know, but I mean, I would assume that it remains as CH3, CH2, OH probably, and you don't get this stealing of your hydrogen, this base acid base reaction. So you would get CH3, CH2, so you get this butanoate ion with, you could say sodium butanoate if you want, and you get ethanol, right? So you get ethanol as well. So this is what we would get. But then they are saying that the products are butane 1-ol and sodium ethanol, but what I'm getting is ethanol and sodium butanoate, which is the opposite thing to what they've written. So I would say 3 is definitely wrong. So I mean 1 and 2 are right, whereas 3 is wrong. So therefore my answer is going to be B. Okay. So yeah. Now let's go to the next question. The compound pentane 1,4-diol has 2 OH groups per molecule and can be oxidized. Which statements about pentane 1,4-diol or its oxidation products are correct? So let me draw out the molecule, because drawing things makes life easier. So pentane 1,4-diol. So it has an OH group on the first carbon atom. I'm taking this as 1, 2, 3, 4, 5. You can kind of, you get the point, right? I'm not going to draw it because it makes things messy to write down the numbers, but it has an OH group on the first carbon atom, and it also has an OH group on the fourth carbon atom. So 1, 2, 3, 4. So also one OH group here. So diol. And 2 OH groups per molecule and can be oxidized. So which statement about 1,4-diol, pentane 1,4-diol, or its oxygen products are correct? When 1 mole of pentane 1,4-diol reacts with an excess of sodium metal, 1 mole of hydrogen molecules is produced. Well, if I reacted with an excess of sodium metal, so this compound plus sodium, right, gives me what? Well, I would get this compound ONA. So I mean both of the hydrogens, because they're both alcohols, right? So both of the hydrogens can be replaced by sodium here. So you get that compound O minus Na plus, with that oxygen, with that hydrogen being replaced, and this hydrogen also being replaced. So O minus Na plus. You could write it as this. Okay. So if I'm getting both of these replaced, that means that I form H2. And now let me just balance this equation. So I used 2 sodium molecules, right? So there should be a 2 Na over here, even though it said excess, but then 2 actually react per molecule, per 1 mole of this pentane 1,4-diol, right? And since I have 2 atoms of hydrogen on the left hand side, I should also have 2 atoms of hydrogen on the right hand side, and I do have that. So that means that how many moles of hydrogen molecules is produced? This is hydrogen gas, you could say. Well, how many moles of hydrogen molecules is produced? I get 1 mole, right, as you can see. So that means that if they're saying 1 mole of hydrogen molecules is produced when 1 mole of pentane 1,4-diol reacts with excess of sodium metal, that is a true statement. So I can say 1 is definitely right. Now, let's see the second statement. At least one of the possible oxidation products of pentane 1,4-diol will react with 2,4-dinitrophenyl hydrazine reagent. So what is 2,4 dinitrophenyl hydrazine reagent? What is that a test for? It is a test for carbonyls. Carbonyls test. 2,4-DNPH is a test for carbonyls, and carbonyl means like CO group, right? In aldehydes or ketones, I don't think it reacts with other carbonyl containing functional groups like carboxylic acids, amides, esters, because those would have, resonance associated stability. However, it does is a test for carbonyls as in aldehydes and ketones. Okay, and would any of the oxidation products of pentane 1,4-diol be an aldehyde or a ketone? Yes. I mean, if you mildly oxidize it with, I don't know, potassium dichromate rather than potassium manganate, and then over only gentle heating, then you could, get an aldehyde such as um, something like this, right? So you could get that. And on the other hand, yes, oxidation of this secondary alcohol would always give you a ketone, right? Whether it's with potassium manganate or potassium dichromate or whatever, with strong heating, but then you would get a ketone. So yes, you definitely do get aldehydes and ketones as possible oxidation products, and because of that, to say that at least one of the possible oxidation products of pentane 1,4-diol will react with 2,4-DNPH is a true statement, because 2,4-DNPH is a test for aldehydes and ketones, and definitely you can get a positive test, because the possible oxidation products, yes, they can be aldehydes and ketones. So I can say that 2 is a correct statement as well. Now if you look at 3, dehydration of pentane 1,4-diol could produce a compound with empirical formula C5H8. Well, I am not exactly sure about that. I'm going to erase this for a while, okay? And I will draw the structure. Whatever I get is dehydration product, basically. So dehydration means I'm dehydrating both of them, and then dehydration of alcohol gives you an alkene product, right? So let me just draw a probable structure. So I could get a double bond here, for example, and a double bond here. Let's do that because that is a possible product, so why not draw it? And now let's see what the molecular formula of this compound is. So I have how many carbon atoms? Because dehydration of alcohol means you're losing water, right? So I'm losing water in this side and I'm losing water on that side. You lose water from an adjacent molecule to form a double bond that is an alkene, right? Anyways, let us count. So 1, 2, 3, 4, 5. I have 5 carbon atoms first, so C5, and then H, how many? 1, 2 hydrogens on this side, and I have 1 hydrogen here, and I have 1, 2 hydrogens here, and then I have 1 hydrogen here, and I have 1, 2 hydrogens here. So how many is that in total? 1, 2, 3, 4, 5, 6, 7, 8. C5H8. So I can see right off the bat that this is true. It can produce a compound with C5H8 as the molecular formula. So 1, 2, and 3 are all correct statements, and therefore my answer is going to be A. Okay, now let's go to the last question. Use of the data booklet is relevant to this question. In an organic synthesis, a 62% yield of product is achieved. Which conversions are consistent with this information? You have 74.00 grams of butanol, giving you 44.64 grams of butanone, and so on and so on. So let me just try out every option here. So butanol is what is going to be, let me just draw the the skeletal formula first, because it's easier for me to draw skeletal formula and then convert them to a molecular formula or whatever. So it's butane, and then you have the O2 here. So it's going to basically be CH3, or let me just make it as C4H. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So H10O, right? C4H10O, that's butanol. Butanone, on the other hand, is a molecule like this, right? So what's the molecular formula? C4 again, H 1, 2, 3, 4, 5, 6, 7, 8, H8, and then O, right? C4H8O. So yeah. And as for butanol, I would assume that's again going to be C4H10O, right? Because it's just an isomer of that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah. Then butanoic acid, on the other hand, is going to be this way. So that's going to be C4 again, C4 H 1 2 3 4 5 6 7 8 O2. All right, and then 2-methyl 1-propanol. Again, I'm going to assume it's going to be C4H10O if I'm not wrong, but I'll just check. C4H1 2 3 4 5 6 7 8 9 10 11 12. Really? Oh no, I made a mistake. I drew, yeah, an extra branch. Okay, so this is 2-methyl 1-propanol. So 1 2 3 4 5 6 7 8 9 10. Yeah, that's right. And then O. Okay, and then 2-methyl propanoic acid on the other hand, I'm assuming that's also going to be C4H8O2, but let's just check. C4 H 1 2 3 4 5 6 7 8 and O2, right? So that is also right. And now let us calculate the moles on the left hand side, and then we'll find the yield, not the yield, but like, yeah, what the amount of product form should be depending on the yield. So let's just calculate the MRs. I will write the MRs, the molar masses, in these brackets, okay, just to make things easier. I'll just calculate it out, and you could do that also yourself. But then carbon, it has a molar mass of 12, hydrogen it has 1.00, and then oxygen is like around 16, right, if I'm not wrong. So using this information, you can just find the molar masses of each one. I'm going to find my calculator. I don't know where I put it actually. So this is fine. I'll just use my phone for now because I don't know where my calculator is and I'm too lazy to find it for question number 40, so why would I bother? But basically, okay, so in butane 2-ol, I have 4 times 12 because I have 4 atoms of carbon. Then I have 10 plus 10 times 1 because I have 10 hydrogens, and then plus 16. So 1 times 16 because I have 16 atoms, sorry, 1 atom of oxygen, right? So that gives me an MR of 74. And again, that's going to be the same for butane 1-ol and also for 2-methylpropan 1-ol because they're the same molecular formula. As for butanone, I'm going to have 4 times 12 plus 8 times 1 and plus 16 because there's 1 oxygen. And so that gives me an MR of 72 molar mass. And then for butanoic acid, that's just going to be plus 16 times, so 2 times 16 or 16 times 2. So that's going to be just plus 16 of the MR of butanone. So that's going to be 88. And then it's going to be the same for 2-methylpropanoic acid, of course. So it's 88. Okay, so now I have all the MRs. Now, what are the number of moles? Well, the number of moles I'm just going to write in a different color, maybe. So N, we know that moles equals to mass over the molar mass, right? So I'm going to do that for each one. So butane 2-ol, I get 74 over 74. That's going to give me 1 mole. As for butane 1-ol, again, that's going to give me 1 mole. And for 2-methylpropan 1-ol, I'm again going to have 1 mole, right? Because it's just 74 over 74. That's very convenient numbers. Okay, now what I want to do is that I know it's a 62% yield of the product. So what I will do is I will find what my predicted. So I mean, all of these reactions have a 1:1 molar ratio. Butane 2-ol to butanone, butane 1-ol to butanoic acid, 2-methylpropanol, propan 1-ol to 2-methylpropanoic acid is all a 1:1 ratio. So therefore, if I have 1 moles of the reactants, then I'm going to have 1.00 moles of butanone, 1.00 moles of butanoic acid. I don't know if my number of significant figures is justified, maybe it should be 4, but anyways, whatever. 1.00 moles of 2-methylpropanoic acid. That's a good thing about MCQs. You don't need to worry about significant figures that much. But anyways, that's what we get. And next what I'm going to do is I'm going to find the predicted mass. So M equals to N times MR. We know that, right? So now I'm going to find the molar mass. So the predicted mass. So the predicted mass should be so N times MR is the moles times the molar mass, so 72. So that means for butanone, I'm just going to make it 1 times 72. That gives me 72 grams. Again, I'm not worrying about significant figures too much. Okay, maybe I should just make it into 72.00 just for consistency with the predicted values, but 72.00 grams. And then butanoic acid is going to be 88.00 grams, of course. And क्या बोलते हैं 2-methylpropanoic acid, you're going to have 88.00 grams again, right? And so these are the theoretical theoretical mass value. So now what I'm going to do is I'm going to check which of these gives me a 62% yield. So this is my theoretical, this column is my theoretical yield column. This is my actual yield column, right? These are actual yield values. Maybe I'll erase the extra thing so that it's kind of more easily now, because now we don't need the extra data, right? We just need the mass values because now we've calculated the theoretical and actual mass values, okay? So all I'm going to do now is erase all of this just because I am impulsive, okay? And so I erased everything else. And these are my actual yields, whereas that column is my theoretical yield. So left hand side I have actual and right hand side I have theoretical. So how do I calculate the yield, the percentage yield? I do the actual yield over the theoretical yield times 100. So I'm just going to do that in each case. So in case 1, I have 44.64 grams over 72.00 grams multiplied by 100, which gives me, yes, it gives me a 62% yield. As for case 2, I have 54.56 grams actually, and predicted I have 88.00 grams, and then multiply that by 100. So yes, again I get a 62% yield, and very much analogously, in case 3, I get 54.56 over 88.00 into 100, which again gives me a 62% yield. So yes, in each case, I get a yield of 62%. So which conversions are consistent with this information? It's 1, 2, as well as 3. And so my answer is going to be A, because 1, 2, and 3 are all right, okay? So yes, that is the last question done, and I hope this paper was useful. It's been a long time since I did a video, so yeah, I know I was stuttering a lot in this video, talking a bit fast, and also might have said some things wrong. So I mean, if there are any things I've said wrong, I would really appreciate if you write it in the comments, and I hope this was still useful, however. And thank you so much for watching.